Okay, so it's a 3:15. So very welcome, a warm welcome from me to all of you joining the first session of the International Conference on Optical MEMS and Nanophotonics. This time in a virtual format of a summer school. My name is Harald Schenk, and I am with the Fraunhofer Institute for Photonic Microsystems and with the Brandenburg Technical University, both located in Germany. I will preside this first session, and before we start with the actual presentations, the head of the steering committee, Dan Maroom, will give a short introduction to this new type of event. Please, Dan.
Okay, thank you. Let me just make myself on the spotlight. Okay, so hope everybody can see me and hear me well. Thank you for joining. We have already 150 attendees, and we have a great number of registrations for our event. Let me launch my brief presentation. Hopefully it works. 1 second. It's giving me some issues right now. Hold on. And nope, 1 second. Let me see why I have some kind of problem. Let me try one thing here, remove the spotlight. I don't know. Okay, hopefully. I don't know why it's not going into PowerPoint presentation, but there's some hiccup here. Let me just try to fix it, and hopefully it will work well for the others as well. I see you do see it a little bit, but not in presentation mode. One second, let me try this. Sorry for this issue.
Yeah, as I said, this is the first time we have this as a virtual format, so this is a typical beginner's issue, but I'm sure we solved that right now.
Well, the PowerPoint presentation is somehow hiding in the background. I don't know.
Maybe you can start just with this.
Yeah, so I'll just mention a little bit. So first, welcome to everybody to the presentation. I hope the presentations will work better for our speakers. We'll make sure to try and fix that. But I want to welcome you to the International Conference on Optical MEMS and Nanophotonics. Our conference actually has a long-standing tradition. It started back in 1996. Back then had a slightly different name called just Optical MEMS. But since then it has been expanded to also encompass the field of nanophotonics as technology matured, and we had the ability to fabricate finer features and enter into the nanophotonic regime. The conference, as I mentioned, has been running since 1996, and it cycles around the world from the Americas to Europe to the Far East, and draws nice attendance every year, bringing in invited talks, keynotes, and contributed talks covering different fields of interest, which relate to the ability to for us as researchers to synthesize structures that will allow us to control and manipulate light with structures that sometimes are actuatable, as in MEMS, or nanostructures that interact with light. The Optical MEMS and Nanophotonics Conference attendee, or the regulars, let's say, have a long-standing tradition of attending these conferences, which are a lot of fun, typically going to nice places around the world, having a great scientific program, as well as...
Dan, sorry,
Yes.
we still see the first slide.
I know it doesn't work for me for
I
some
see.
reason.
Okay, sorry.
And I don't know why PowerPoint is acting up, but it just is. Let me just try one more thing, but it is simply not going into presentation mode. Not sure why, but hopefully it will be better for the others. So, as I mentioned, conferences are around the world and a great lot of fun. And this past year, due to the pandemic, of course, we had to cancel the 2020 event, which was last year. And since this year was not shaping up to be in much better shape, we decided to try something different. And hence we have this new format, which is the online summer school format. And I want to thank the steering committee for suggesting speakers for the event, and then having the suggested speakers that were, of course, willing to join the school. We've broken up the event to 3 different days, and in for not trying to keep the focus, we just limited to a specific 3 hours per day at a time slot which hopefully fits most of your time schedules. I know it's impossible to have everybody at the same time working together, but this is the limitation of a global conference as this. I see some messages here. I know all the tricks how to get the PowerPoint to work. It's not working, so please bear with me. So before jumping over to the main event, the speakers of the day, I also want to thank the IEEE Photonic Society for having a long-standing collaboration and support for the Optical MEMS and Nanophotonics Conference. In the past, they have been technical co-sponsors of the event, and with that support, they were also able to distribute the announcements for the event, as well as post the proceedings on IEEE Explore. For this year, since we're going to this new format of this summer school, then we have slightly different settings, and they have also offered their support, and we thank them for that. I also, unfortunately, cannot show the PowerPoint presentation, but I'd like to also mention that we have scheduled for next year's event, which hopefully will be in person and will be in scheduled to be in Brazil, and that is, of course, depending on the health and travel situation around the world. So we do look forward to having the event hosted in person, as our typical year after year events have been in Brazil next time, and hopefully we have convinced you all of the interesting activities and science and technology aspects that we cover in the conference, and you will consider, of course, coming to this in-person event. Lastly, I want to mention that we have a great program, 3-day program, 3 hours per day, devoted to 3 different topics, as you know. The first is what we'll be discussing today, which is covering the topic of photonic computing systems, and we have a great lineup of speakers. Unfortunately, my slides don't show them right now, but you've probably seen them all on the website. And we have 2 more exciting days, tomorrow and the following day. So on Wednesday, we'll be talking about meta surfaces and their intrinsic limits, and we have also great speakers there. And finally, the last day, we'll be talking about sensors, biophotonic and nanophotonic sensors, and again, a great day scheduled there. So with that, I'd like to return the screen now to Harold, and hopefully we'll get the technicalities sorted out, and we'll enable Mark to try and turn his video on, as well as hopefully the presentation will work for him much better than it did for me. Thank you.
Okay, thank you, Dan. I'm not sure if my video can be seen now or if it's still yours because you're still highlighted.
I believe yours is showing, and I can put a spotlight on you.
Okay, great. Now it works. Right. Excellent. So thanks, Dan. And let me add that actually you put a tremendous amount of effort in preparation of this conference here. We tested everything but to share slides. So that's a real pity. But okay, that's how life is. Right. So our first session actually focuses on recent developments and outlooks of reconfigurable photonic computing, which is a highly exciting and important field of photonics and is actually constituting a pillar for next generation computing. There are a lot of very interesting approaches in academic research and lots of very interesting activities of companies towards commercialization of the latest research results. And therefore, I am very pleased that in this session, we have the chance to learn more about recent activities, views, and insights from both sides. We have 3 invited talks and 1 keynote presentation. Before we will actually start with the presentation, there will be time for questions. Please use the question and answer window at the bottom. And please, this window only, because otherwise it will be very complicated for me to collect the questions if I have 2 different windows. So use the question and answer window, write and send your questions to me. I will collect and address them to the speaker after the presentation. We will now start with our keynote, and it's my great pleasure to introduce to you Professor Mark Thompson, who will talk on photonic quantum computing. Mark Thompson is a co-founder and chief technologist of PsiQuantum. He has over 20 years experience in the field of integrated photonics and quantum technologies. He holds a PhD from Cambridge University, and he held positions at Toshiba, Corning, Bookham Technology, PsiQuantum. He holds a professorship at the University of Bristol and a fellowship at the University of Cambridge. He established and was director of the Bristol Center for Quantum Engineering and the Bristol Quantum Technology Enterprise Center. And he also holds prestigious UK and European fellowships and prizes. He published more than 100 papers and patents, and he has founded 2 startup companies in quantum technologies. Mark, we are looking forward to your presentation.
Hi, thank you. Thank you for the nice introduction, and thanks to Dan, Harold, and the rest of the team for giving me the opportunity to speak here today. Okay, I'm going to attempt to show my slides and see if we are successful or not.
Well, it worked for you. Wonderful.
Yeah, so you see full screen slides?
Yes.
Yes, perfect.
Right,
thank you.
Excellent. Good. All right. Yeah, just adjusting slightly here. Okay, well, good morning, good afternoon, good evening. I guess everyone's in different time zones. And yeah, like I said, it's an absolute pleasure to be here today to have the opportunity to speak to you about my favorite topic, which is quantum computing and integrated photonics. And you know, of course, quantum computing these days is a very hot topic. Governments are investing billions of dollars into this area. We just had some recent announcements from Europe where France and Germany collectively were investing over 3 billion into quantum technologies. There is a host of the big multinational corporations all have very serious efforts in bringing up and developing quantum computers, so Google and IBM and Intel, Microsoft and Amazon, as well as a growing body of startup companies, of which I'm fortunate enough to be a co-founder of one of them. So the race is well and truly on, and it's our belief that photonics will play an absolute central role in quantum computing, and it's also our belief that photonics really has the potential to win this race in terms of developing this absolutely sort of outstanding and crucial technology. So in the talk today, I'm going to go through sort of the introduction with a general introduction to quantum computing, just to sort of set the scene and the context so you understand why people are so interested in this technology. I'm going to talk to you about how photons and integrated photonics can be used to realize large-scale fault-tolerant quantum computers. I'll talk a bit about the manufacturability and the scaling of those systems, and then I'll tell you a bit about the hardware that we've been developing at PsiQuantum towards that goal. So, hang on my slides there. There we go. So yeah, so we're PsiQuantum. We're a 5-year-old startup company based in the heart of Silicon Valley in California. We're now about 150 in staff. For those watching the news closely, you may know that we just announced our Series D investment, which was just over $450 million invested into the company. And the sole focus, goal, mission, and purpose of the company is to build the world's first large-scale, fault-tolerant, error-corrected quantum computer. And large-scale, fault-tolerant, error-corrected is just a long-winded way of saying useful. We are building useful quantum computers that can deliver meaningful applications and solve problems. Quantum computers, we believe, are one of the world's most, well, it's going to profoundly change the world in terms of what quantum computers will enable. It will take impossible problems and make those problems possible. It's really a completely new way of doing computation. So it's not just an improvement on conventional compute. It's not a faster microprocessor or a bigger data center. Quantum computers operate in a completely different way and really allow us to solve problems that would have otherwise forever remained unsolvable. So profoundly world-changing technology, maybe not as profoundly world-changing as, say, fire or agriculture or maybe the wheel, but we really believe that quantum computers will propel humanity into a new era of innovation and technology development. And this concept of quantum computing and what it could do was really first realized way back in the 1980s by a famous physicist. I'm sure you all know Richard Feynman, and he made the observation that the world around us is quantum mechanical, and that if you want to really simulate and understand the materials and physics at a deep level, then you need to simulate those systems on quantum mechanical machines. So he really made the observation that to efficiently simulate physics and quantum systems, you need to do that on another quantum system. And that really was at the heart of, when people started to think about the prospect of using quantum machines to perform computation. And, that really came to light by, in the 90s by observations of people like Ralph Landau, who really understood and codified the concept that information is physical. And once you understand information is physical, and the fact that, any information that we have always has a physical representation, whether it's the let's say the chemical imbalances in our brain that represent our memories, or the ink on a paper of a note that you've written to yourself, or the electrons within a memory cell inside your iPhone. Any information that we have always has a physical representation. And that information, if you want to process that information, you must use a physical process to process that information. And of course, these concepts, we understand in the terms of classical computers and the computing machines that we have today. But of course, physics and nature at its heart is quantum mechanical. And so this whole principle, are mapped onto quantum information. And so with quantum information, if you have information in a quantum state, then to process that information, you need to use quantum processes. And this is really where the whole idea of quantum information processing comes from. Can we tap into those, let's say, laws of physics or tools of physics that we don't otherwise get access to in our everyday interaction at what we call the classical level of physics? And so it's really these quirky properties of quantum mechanics, of superposition and entanglement, is what we exploit in terms of getting this exponentially greater compute power out of quantum compute technologies. And so, so in terms of what does that mean? If we look at kind of classical bits, of course, a classical bit exists in either the 1 state or the 0 state. Now, if you have a qubit, by the quirks of quantum mechanics, that bit can be both in the 1 state and the 0 state at the same time. And this is what Schrödinger referred to when he was torturing his poor cats, whether they were dead or alive. And you can take this a step further. Something even more, say, weird and obscure is the idea of quantum entanglement, where now you have 2 quantum particles, and those quantum particles, you can entangle them such that they have an intrinsic connection with each other. So no matter how far apart you separate these 2 particles, there are these correlations between the particles that cannot be explained by the laws of classical physics. We call that entanglement, and it's these properties of entanglement and superposition that we exploit when designing quantum algorithms and running quantum computers, and that ultimately lead to this incredible speed up for certain problems and certain applications that we want to solve. So just to put that into a little bit of context of, what does it mean, like exponential speed up? It's very hard as humans to understand what exponential means. It's, I guess now we've been through the pandemic, and I think we're all a little bit more familiar with what an exponential trend looks like, but there are very few things that actually follow exponential trends. And as an example here, we've got, this is Telluride. It's one of the world's most powerful supercomputers. And with all of the might and megawatts of electricity required to run Telluride, it can just about simulate my favorite molecule. This is a caffeine molecule, has about 30 atoms. And if we take this caffeine molecule and perform a full quantum mechanical simulation of this molecule, if we added on 1 more atom to our caffeine molecule, it would now require 2 Tellurides to be able to simulate that system. So we add just 1 more atom, but the complexity of that system grows exponentially. If you want to do something a little bit more complicated, and this is a molecule used in the treatment of hematological cancer, it's about 100 atoms in size. So we've gone from 30 atoms of caffeine to 100 atoms of this protein for drug treatments. And now to simulate that would require 1,000 billion Tellurides. So the problem just explodes. And before you know it, the compute resource that you need is larger than all the atoms in the known universe to solve some of these problems. So problems like this are not just hard problems to solve, but they're problems that are forever out of the reach of classical compute machines. However, problems like this are solvable on a relatively small, relatively modest quantum computing system. And so some of the very early applications of quantum computers are looking at exactly these sorts of problems. Now, quantum computers are not just limited to the simulation of my favorite molecules. There are applications across all of science and technology where people have developed and discovered quantum algorithms that give meaningful speed up. So things in like quantum chemistry and quantum simulation, in areas of linear algebra, code breaking, the Shor-Spatring algorithm, another very famous example, as well as areas across machine learning, search algorithms, so on and so forth. And it's for all these reasons that all these governments and all these companies are so interested in quantum computing, because of the potential breakthroughs that quantum computers will enable. So at PsiQuantum, we are particularly focused on a number of key verticals in terms of our interest in the applications of quantum computing. So across climate, healthcare, energy, and the high-tech sector. And the founders of the company are particularly passionate about using our quantum computers for good. And in terms of solving some of the most pressing problems that are facing humanity, and it's hard to imagine a problem more pressing than climate. So we would love to see ours and future generations of quantum computers being used to tackle some of these really key problems. In terms of designing algorithms to run on quantum computers and to solve certain problems, if you look inside the kind of algorithmic development process, there are just a handful of, say, quantum computing subroutines that are used that give the sort of the speed up, you know, all the ones that we've discovered at least. So things like the Grover algorithm, quantum walks, Hamiltonian simulation, phase estimation, Fourier transforms, and so on. And combinations of these core subroutines are used to form the zoo of quantum algorithms that we have. And these algorithms fall typically into different categories. So here's just examples of how those algorithms or those subroutines combine to give, you know, different algorithms for different applications. So we have these graph theoretic problems for solving things like, you know, traveling salesman type problems. There are the linear algebra and differential equation algorithms for use in things like simulating fluid dynamic systems. There are the search and optimization algorithms for, like, you know, doing searching databases, derivative matching, these sorts of things. There is the more speculative area of quantum algorithms for artificial intelligence and machine learning. And then here are those more sort of physics-based applications, so the simulation of quantum chemistry, material science, high energy physics, condensed matter physics in that quantum simulation regime. And it's really this regime of quantum simulation is where we think the most impactful short-term applications will come. And in terms of targeting meaningful application areas like climate, for instance, you know, quantum computers will have applications across all of these different aspects of climate, but particularly in those areas where new materials discovery or new chemistry is critical. And I'll just give a couple of examples of these three areas, just to give you a little bit more of a feel for, you know, what that means and what quantum computers could do. So one area is in high temperature superconductors. And so, you know, to date, we do not have a general theory of superconductivity, and progress in this space of trying to discover higher temperature superconductors is really limited by very experimental methods. And, you know, what could we do with high temperature superconductors? I think, you know, there's a huge array of potential opportunities with these. In the space of climate change, it's maybe surprising to know that about 30% of all electricity that we generate is lost in the transmission of that power across transmission lines. And so we could save huge amounts of the global energy by using high temperature or lossless transmission lines. So there's a lot of motivation to, you know, to look and develop these materials. And, you know, quantum computers are well positioned to be able to simulate the physics that goes into these superconducting materials, and hopefully unlock and provide insights into delivering these high temperature superconductors. Another area is that of fertilizer production. Rather surprisingly, producing fertilizer consumes about 2% of total global energy and about 5% of our natural gas production. And it uses this very industrial, this old process called the Haber-Bosch process, which requires high pressures and high temperatures to fixate nitrogen to form ammonia fertilizers. However, we do know that it's possible to do this at room temperature and atmospheric pressure, because we know bacteria that are able to do this nitrogen fixation very, very efficiently. We just don't understand how it does it. It uses this enzyme called nitrogenase and this cofactor at the active site of nitrogenase. And algorithms have been proposed to simulate the FEMICO cofactor and on a quantum computer. And if we could simulate that and understand how it works, we may be able to unlock the secrets of this catalyst and figure out how to make fertilizers much more efficiently and potentially more abundantly. And my last example here is one of electrification of our transport system. You know, currently about 10% of all greenhouse gas emissions come from our gas guzzling electrical vehicles. So if we could replace all of them with electric cars, we could really help target those carbon reductions that we're looking for. But when it comes to electrification, car batteries are a real bottleneck. And right now, we really still don't understand the underlying chemistry of some of these electrolytes in things like lithium-ion batteries. We've teamed up with Mercedes-Benz. We've worked on this problem with them. We've developed algorithms and for the simulation of the electrolyte chemistry within lithium-ion batteries, and estimated, the resources required to do that. And it's hoped that early-stage quantum computers can be used to make more efficient batteries for longer range, better safety, better cost, better lifetimes, and really accelerate that electrification of our transport system. And so, at this stage, you're probably thinking, "Wow, that's a lot of very useful applications that we can do with a quantum computer." But how big a quantum computer do you need to be able to run these sorts of applications? Well, if you look at the paper we did with Mercedes-Benz, we did go and plot the resource requirements for a whole host of different algorithms and applications. So in this plot here, you see on the x-axis the number of logical qubits within your system. On the y-axis, it's the number of computational gate operations required to perform that algorithm. And here you see in yellow our work that was done by Amazon on the Fermi-Hubbard model, looking at how you could simulate high-temperature superconductivity. And there's applications coming out of sort of a couple of hundred qubits with about 1 billion computational clock cycles. The work done by Google looked at this Fermico molecule for nitrogen fixation. And we, with Mercedes-Benz, looked at those resource requirements for doing the simulation of the electrolyte chemistry within lithium-ion batteries. And so you can see that the kind of resource requirements that you need are quantum computers in the range of hundreds to thousands of logical qubits with billions of sequential gate operations. And the development of these algorithms over time are improving as we discover new ways to run these algorithms, as we optimize these algorithms. And so we're seeing that the resource requirements are coming down all the time. But I think it's fair to assume that we're not going to hit resource requirements really that go much below the 100 qubit regime. So in terms of your minimum viable product, a machine that can outperform the most powerful supercomputers on the planet for meaningful applications, we really need quantum computers of around 100 qubits. And so if you've been following the news, you may be quite excited to see, well, wow, we're not that far from 100 qubits, so we're really not that far from unleashing all of these potential applications. And in fact, you'll have seen in 2019, Google released their quantum supremacy chip, which is a 53 qubit superconducting processor. And they used that to perform a benchmarking algorithm, a quantum supremacy algorithm, and were able to outperform this machine, which is currently the world's most powerful supercomputer. It's the Oak Ridge Summit computer. It consumes about 13 megawatts of power and has about 40,000 CPUs within it. And that was a very, very impressive demonstration. And more recently in 2020, the Chinese University of Science and Technology did something very, very similar using a photonic approach to quantum systems. And with both of these systems, although they do move into this regime of quantum supremacy, they don't really do anything useful. These are really benchmarking applications. And when we say we need hundreds of qubits, what we really mean is we need hundreds of usable qubits. And by usable qubits, we mean error-corrected logical qubits. A quantum computer is a kind of hybrid digital analog system. It's digital in the sense that when you read out your qubits, they're either in the 1 state or the 0 state, but it's analog in that before you read those qubits out, they're in this superposition state between 1 and 0, and they're very susceptible to noise. Now, fortunately, we can combat the noise within these quantum systems through error correction, but the overhead to do that is actually very large. And so it turns out to get one usable logical qubit requires of order thousands of physical qubits. And so our minimum viable product really is a system comprising of millions of physical qubits. And that, with error correction, allows us to distill out hundreds of logical qubits that can perform billions of sequential gate operations. So the machine that Google produced, that sits in this regime of noisy intermediate scale quantum systems, it had 50 odd qubits, but it could only perform of order tens of operations before the noise within that system built up to the point where it was just spitting out random errors. And so about 10 to 20 operations is what's possible within those machines. If you can implement error correction, then you can do calculations for millions to billions of sequential gate operations. And that's where you need to be to do all known useful applications. So this whole concept was put together quite nice in this graph from Google, where they showed that the number of qubits that you need on the x-axis, the error rate of your individual qubits on the y-axis, and then you have this purple regime where we can perfectly well simulate the behavior of that system classically, and you're not doing anything that you couldn't do on your laptop. You move into this sort of purple bluey regime, where you move into these noisy small intermediate scale systems where you can demonstrate quantum supremacy, but not for useful applications. And it's really not until you get all the way out to this green regime where you can implement error correction and really do useful applications. And that was very nicely summed up in this 2019 National Academy of Science report on quantum computing. There was a lot of hope that there would be useful applications in this NISQ regime. There may still be some very, let's say, narrow applications in this space, but a general purpose, generally useful quantum computer requires error correction. So there are many different approaches to quantum computing, many ways to realize your qubit technologies. So some of the most popular are ion trapping and superconducting systems. There are other systems like quantum dots and Majorana fermions and the photonics approach that we pursue. And they're all pursued in a very serious way by many of the companies that are out there. But what is maybe rather surprising is that although there are many, many different approaches to the hardware approaches to quantum computing, they really break down into two very, very broad categories, those that are based on matter and those that are based on light. So on matter-based qubits, they use electrons to represent the quantum information within that system. So that could be the energy levels of an atom trapped in an electromagnetic field. And in the photonics-based approach, we use the various degrees of freedom that single photons have to offer. And so why might one want to pursue a photonic approach to quantum computing? Well, there are a number of real, let's say, key benefits that photons bring as a qubit. The first one is that they're very robust in that they are massless relativistic particles traveling at the speed of light, and they don't interact very well with themselves or with the environment. And so photons don't decohere, they maintain their quantum state until, for instance, they get absorbed. Photons are very easy to manipulate just using standard optical components. They're very, very fast to measure, so your systems can run at very, very fast clock speeds. They're natural carriers of quantum information. So if you want to transmit quantum information, you can use photons down fiber optics as an example, and that's a natural way to scale up your quantum systems. Photons can work at any temperature, so they're not restricted to these cold millikelvin temperatures, and that's really an offshoot of the fact that they're very robust and don't suffer these environmental fluctuations. And light is also manufacturable. We have a very well-established photonics industry and integrated photonics industry out there, and 90% of the technologies and components required to do photonic quantum computing already exists and already used in commercial systems. There's always a downside. There's always the but, and the Achilles heel for photonic photons as qubits is that it's hard to entangle photons. It's hard to make photons interact with each other. This is one reason why they're such good isolated qubits, because they don't interact. But of course, when you want to do an entanglement, you need to make your photons interact. And that's part of what we've at PsiQuantum have spent an awful lot of our time doing, understanding how to make photons interact with each other efficiently. And so if you look at the requirements to build a quantum computer, you need 2 qubit gates, single qubit gates, low noise, fast speeds, connectivity, favorable operating environments, and manufacturability. And it's clear that matter-based systems are much easier to entangle and implement these 2 qubit gates. But you can argue strongly that photonics really excels in all the other metrics of interest. Okay, so how do we encode our quantum information onto photons? Well, you can, in principle, use any degree of freedom that the photon has. You can use its color, its time of arrival, its polarization, its mode shapes, any degree of freedom that you have control on. You can use that to impart quantum information onto that photon. One of the most popular ways in the area, one that we focus on, is this path encoded approach to encoding our photons. And so, let me just try. So yeah, so in this situation, what we do is we have two waveguides as an example, and a photon in the top waveguide represents the 0 state, and a photon in the bottom waveguide represents the 1 state. And we can move into this superposition of being in a 1 and a 0 state at the same time by simply using a beam splitter. And so now our photon passes through the beam splitter, and it's in the upper path and the lower path at the same time. Now, of course, if this was bright light, this would be meaningless. It would just be a 50% beam splitter. But when you're operating at the single photon level, you cannot split your photon in half. It moves into this quantum superposition state. Now, once we have our qubit encoded in path, we then want to be able to manipulate that qubit state. And we can do that using very simple Mach-Zehnder-like components, where these alpha, beta, and gamma phase shifters allow us to move from any point to any other point on our block sphere. So we can take a qubit state from the 0 state to the 1 state or into the superposition state by just manipulating these phases. So very simple to control, prepare, and manipulate single qubit states. Now, to build a quantum computer, you don't just need single qubit operations, you also need 2 qubit operations. And in this situation, you take your 2 qubits and you interact your qubits together. And these gates are typically used to perform entangling operations. And to do that, you effectively require a single photon nonlinearity. And there are many ways in which people have explored implementing single photon nonlinearities, and particularly using matter to mediate this photon-photon interaction. And there are proof of principle demonstrations out there. They are all technologically very hard and very inefficient. And for a long time, it was thought that this was the killer blow to photonic quantum computing, that you need this single photon nonlinearity. And how can you do this efficiently and at scale? So it was a real big question for a long time whether it was even possible to do photonic quantum computing. That was until about 2001 when Camille Flammert-Milburn made the discovery, the theoretical discovery, that by using additional single photon detectors, additional photons, and a network of linear optical elements, so just beam splitters and phase shifters, it was indeed possible to use something called a measurement-induced nonlinearity at the single photon level. And that large-scale universal fault-tolerant quantum computing was indeed possible with these systems. And so with just single photon sources, ways of manipulating those single photon states, so beam splitters, phase shifters, Mach-Zehnder interferometers, and single photon detectors, it is indeed possible to make a universal error-corrected fault-tolerant quantum computer. Now, the initial proposals put forward for this were based on the circuit approach to quantum computing, and the resource requirements were astronomical, really. It looked okay in theory, but in practice, the numbers required to build these systems was very, very large. On top of that, when you made your computations longer, you made the circuit depth longer, and loss very, very quickly became a problem. More recently, this circuit-based approach has been mapped to this cluster state approach to quantum computing, which is much more amenable to implementation with photons. And in this cluster state approach to quantum computing, what we're effectively doing is creating this net of entangled photons. So each dot you see is a photon, and each photon is entangled with its nearest neighbors. And to perform a computation on this, what we do is we go through this net of photons, and how we measure these photons or these qubits determines the computation that we perform. And so pictorially, what we're looking at here is a system that generates a net of these entangled states, and a system that then measures out these entangled states in a way to perform the computation. And sort of visually, what we see here is 2 logical qubits. Time is in this sort of up and down direction, And at this point here, you can see that we're performing an entangling operation between these two logical qubits. So these large clusters of single photons represent our logical qubits. And so the machine that we're building, the quantum computer we're building at PsiQuantum, comprises of these arrays of photon sources, these active interferometers that entangle these photons into these nets of, let's say, clusters. And then these cluster states are then detected and measured at the output. And so the way that we can generate these clusters are we can take single photons, and then we can go through fusion operations to fuse these together to form small resource states. And then these resource states can then be fused further and computations performed upon those resource states. And the operations to do these fusing operations are actually really quite simple. We can use simple networks of beam splitters to take single photons to form entangled pairs. We can take those entangled pairs of photons and we can fuse them together, in this case, to make a larger 3-photon entangled state. And we can take that even further. We can then start to fuse these together to create, as an example here, a 4-photon entangled state. So it's these sorts of very, very simple circuits of just beam splitters and detectors that can be used to fuse these qubits together. And so proof of principle experiments in these sorts of things have been done over the years using traditionally bulk optics approaches, so tie sapphire lasers, BBOI crystals, large arrays of beam splitters and phase shifters. And at PsiQuantum, what we're doing, is looking to scale that up. There's no way that system will scale to millions of qubits. The only way you're going to scale is leveraging integrated photonics and the manufacturing of the semiconductor industry to do that. So at PsiQuantum, we're looking to integrate photon sources, photon manipulation, and photon detectors all within a single coherent system. I'll just say a little bit about how we achieve this technology. So in terms of photon generation, we're using the intrinsic chi-3 nonlinearity of these photons of the materials of silicon and silicon nitride to generate spontaneous photons. And then those spontaneous photons we can detect and herald off those photons, and that forms individual resource of photons that we can use. And we can use things like microring resonators to improve the performance of these devices. Probably the most interesting and unique device is the single photon detector, where we can detect just attowatts of energy of single photons. They are superconducting in nature, so they operate at around 4 Kelvin in temperature. And effectively, it's a very, very thin wire of superconducting material that when it absorbs a single photon, that energy breaks the superconductivity of the wire, forcing it from zero resistance to mega resistance in just a few picoseconds. These are incredible detectors, probably the most sensitive detectors that you can get, and really a very enabling technology for this whole integrated quantum photonic platform. And then manipulation of photon states is really quite straightforward using these sort of Mach-Zehnder structures. And here's an example of a Mach-Zehnder structure that was highly balanced so that we could achieve over 60 dB of extinction ratio and really prove out that we could get these incredibly low 10⁻⁶ errors of control on single qubits. And so these and similar sort of circuits have been demonstrated at length in academia. And over the years, we've seen this increased scaling of the technology from just a few components on a chip to now up to 1,000+ components on a single chip. But still, a lot more scaling needs to happen to get to the size of systems required to deliver a useful quantum computer. And the routes to scaling really are one of increased integration density and qubit interconnection. Now, in terms of scaling, connecting qubits together, systems together through a qubit interconnect is a natural way to go. And that technology is readily achievable in photonics. Here's 2 examples. First example showing entanglement generation in a chip and distribution of that entanglement between 2 chips using path to polarization qubit converter. Here's another example, more complicated, where quantum teleportation was performed between these 2 chips. So scaling through interconnects in photonics is relatively a trivial thing to do. Scaling through integration is really where PsiQuantum has put an awful lot of focus. And it's our belief that to get to the levels of complexity that we need, the only way to do that is really leverage the manufacturing capabilities of the advanced CMOS industry to get to the levels of performance, yield, and component densities that we need. And so PsiQuantum has really, we've focused very much on getting into that regime of moving away from university fabs and 200mm fabs, getting into those high-end 300mm CMOS fabs. And as of a year ago, or as of 2 years ago, we teamed up with Global Foundries, and as of 1 year ago, we've had devices now being manufactured in the commercial production lines in upstate New York. And what you're looking at here is a 300mm wafer that has a 25-layer stack. It has over 500 process steps. We've put 6 processing tools into the production line at Global Foundries to enable this technology. And on that wafer are thousands of single photon sources and thousands of single photon detectors. And we've now processed thousands of wafers through this development process with Global Foundries. And of course, people have built single photon detectors before, but not in a commercial CMOS process, the same process that is churning out millions of chips for cell phones and laptops and so on and so forth. And why move to this 300mm process? In part, it's really the control and precision that we can get. A key metric, as an example, is the lineage roughness of either your waveguides or your detectors. And what we've observed by moving from 200mm to 300mm fabs is things like the pattern fidelity. We get improvements of up to 5x in the pattern fidelity, and that translates directly through to improvements in device performance. So here we can see in blue the low pattern fidelity of the single photon detector and the improvements in performance we get by moving to these much higher end processors. The lower lineage roughness of your nanowire detector allows us to get much more efficiency out of these devices. And so here's an example of one of those devices that we've fabricated, superconducting single photon detector. We have these walls around the detector to protect it from scattered light. And of course, we've not just made one of these detectors, we've made thousands and thousands of these detectors. And here's an example on the right showing hundreds of these detectors characterized with over 98% of these devices giving greater than 90% efficiency. And on the right, you can see the levels of precision and control that we can get. The width of these nanowires is varying by just 1.4 nanometer from wafer to wafer, and the thickness of those films is varying by less than an angstrom from wafer to wafer. So real incredible levels of precision and control. Now, I've just told you about the chip technology that we've been developing, and of course we've done similar development across the photon sources, the filters, the waveguides, the switches, and so on and so forth. In terms of the rest of the system, we have also invested heavily in building the full system, so the control electronics, the optical I/O, the packaging, and the assembly that surrounds this whole chip. And so in our first generation systems developed with Global Foundries, we are also integrating the electronic chip with the photonic chip through a hybrid bonding process. We've also integrated of order 200 port optical fiber arrays for large optical port input-output within these systems. And what you can see here is an example of that electronic chip that we bond to that photonic chip. So this operates at cryogenic temperatures. It's a standard 22 nanometer CMOS process, also at Global Foundries, and it contains about 750 million transistors. And through this hybrid bonding process, we can connect with thousands of electrical connections between the photonic chip and the electronic chip. So in terms of the sort of challenges to scaling that we see, manufacturability, cooling power, connectivity, and control electronics are the key manufacturing scaling challenges that we see. And we believe that we're really tackling these problems very effectively with our photonic approach through leveraging tier 1 CMOS fabs, through leveraging the more higher temperature cryo systems where we can get kilowatts of cooling power at 4 Kelvin with large commercial systems, connectivity through standard optical fibers, and these integrated CMOS chips for advanced control electronics. Maybe in terms of scaling, one more thing to point out is that using fiber optics gives us a really unique advantage, not only in connecting systems together, but by having our qubits within fiber optics, we can also use our fiber optics as an effective quantum memory where we can store qubits in long arrays of fiber optics. We call this quantum interleaving. There's a paper on the archive if you want to read more about it. But what it effectively allows us to do is create cluster states that sit inside a fiber optic a delay line, and we can get of order 5,000-fold reduction in the resource requirements of our machine by moving into this kind of quantum interleaving regime. So very unique to a photonic approach to quantum computing. And so really just drawing to a conclusion now, I hope you have an appreciation now as to what is required to build photonic quantum computing and how it contrasts to other technologies. We are focused very much on a manufacturing approach to delivering this technology. We've developed the fault-tolerant architecture that goes alongside that, and we have these realistic approaches to scaling in terms of the temperatures that we're operating at, the use of interconnects and fiber optics, and the manufacturability of our technology. And so with that, I will just jump straight to the conclusion as I'm a bit short on time and say thank you very much for listening.
Okay, thank you very much, Mark, for this fantastic journey through photonic quantum computing. There is a couple of questions here, and let me see. So the first question here is regarding the applications. So the question one is, how can quantum computers help in developing room temperature superconductors? And there is a similar question which addresses the possibility to apply quantum computing to optimize fusion. So not nuclear fusion, but sun-like fusion.
Yeah, no, both great questions. So they're both very related, right? So it's about using quantum computers to simulate physics. So it goes right back to Feynman's observation that the best way to simulate quantum systems is to use a quantum system, and both fusion reactions or high temperature superconductivity very much fall within that regime. And the systems where you get a high electron correlation is typically where quantum computers really excel. And so when you look at a superconducting system, you're looking at many electrons that are effectively operating in a single coherent state. And simulating those sorts of systems on classical computers is virtually impossible. Whereas there's a lot of hope and anticipation that quantum computers can much more readily simulate those systems at scale. And there's been some examples done by Amazon where they've looked at the Fermi-Hubbard model, which is a kind of proto sort of model for these sorts of systems. And so there's speculation that sufficiently powerful quantum computers could help us really produce models and simulate different materials rather than doing it, let's say, very experimentally and practically right now. And similar with fusion, and particularly with fusion, I think a lot of the potential interest there is around simulating the kind of the plasma and the plasma properties of these reactors. But there are also other areas where developing new materials, new radiation hardened materials that goes into developing these fusion reactors. So it's really all about the development of new materials and really understanding and simulating accurately these complex correlated systems.
Okay, thank you. There's another class of questions regarding error correction. So the one question is how this is actually implemented in quantum chips. So obviously it's not done with classical programming based on interpreter, compiler, or the else.
Yeah, so it's very different from the way error correction is done classically, but effectively when we read out the quantum states, there is then a processing that needs to be done on that information. And so we have a classical processor that sits very close to the photonic chips that interprets all that data, runs it through the error correction algorithms. We call it a decoder. And then based on the results of that decoding, we then reconfigure the optical circuitry and read out the states in a different basis next time. So so it's not the sort of thing you can explain in just a couple of minutes, but it really is about that kind of feed forward and dynamic reconfigurability of the circuit depending on what states you got in your previous time steps.
Okay, thank you. Let me add another question regarding error correction. Is there actually a fundamental physical boundary limit, or is it just a question of technical realization to further reduce errors?
So everyone's qubits surprisingly seem to be roughly landing in the same ballpark in terms of the number of errors. Everyone is getting into the regime of around 3 nines, so about 0.1% in terms of the error of a physical qubit. And that really limits very quickly the number of computational operations that you can do. You really need a logical qubit to have an error of about 10 to the minus 12. To get really into that useful regime. And the only way you can get to that level is through multiple rounds of error correction. So maybe if you tried really, really hard, you could reduce to 10 to the minus 4 for your single qubits, but it still is a long way from where you need to be to do practical applications.
Okay. Yeah, thank you very much again, Mark. There are a couple of further questions actually in the chat and in the question and answer window. So sorry if I'm not able to address all the questions now for sake of time. So thank you very much again for this great talk, and we will have to move over to the next one. Pardon?
Harold, let me just interject for a second. Mark, I mean, you finished your talk, but I think you can answer offline some of the questions, and then people see that, then at least they can get an answer to their questions.
Very good hint. So please make sure to check both the question and answer and the chat. And I'd like to ask everybody once again, please put your questions in the question and answer window only. That makes things a bit easier. Okay, thanks for the hint, Dan. We will now move over to the next talk, and it's my great pleasure to welcome and introduce Professor Ali El-Shari, who in this invited talk now will present his work in hybrid quantum photonics. Ali is an associate professor at the Applied Physics Department at the Royal Institute of Technology in Sweden, and his research focuses on hybrid quantum integrated photonics, with the goal of realizing novel high-performance quantum circuits for communication, sensing, and metrology, which will leverage the quantum nature of photons. He received a number of research grants, including VR Starting Grant from the Swedish Research Council, Marie Curie Individual Fellowship, a track grant from EU Horizon 2020 for developing breakthrough technologies for science and society. Ali, please begin with your presentation.
So thank you so much for inviting me. It's actually hard to top Mark's talk, but I tried my best to try to give you another perspective of hybrid integration now in quantum integrated photonics. It will not be in the same level of scaling as Mark showed, but I'll show you the recent research efforts. So in quantum integrated photonic circuits, there has been a great progress, but there are obviously some of the challenges that Mark highlighted in a previous talk. And if you would like to characterize quantum integrated photonics, you can roughly put them in 2 main categories. The first, depending
Sorry
on
to interrupt.
Yes?
There's no slides to be seen.
Oh, really? Okay. Let me try again. Now?
It's coming.
Yeah, okay, thank you. That works.
Yes. Yeah, so again, if you would like to characterize quantum integrated photonic circuits based on the sources that is used to generate the single photons, you can put them mainly in 2 categories. You either use nonlinear effects to generate the single photons as the approach that Mark showed based on Chi2 or Chi3 nonlinearities in silicon nitride, aluminum nitride, or silicon oxide waveguides. So there are different advantages and disadvantages of using this approach. You can integrate detectors quite efficiently. You can operate at telecom wavelength. You don't have an access to solid state qubits, so you can use other approaches like, for example, the fiber loops that Mark used. But the problem also is that the sources are not on demand. So the source is probabilistic. So we have a Poissonian distribution for the photon pair generation because it depends on the nonlinear effect in that material. And there is also the other types of quantum photonic circuits based on atomic-like transitions, like in quantum dots, Kähler centers. And these have the advantage of having on-demand emission, but they have some issues like, for example, the difficulty to scale up the circuits and the low efficiency typically for detectors integrated in these circuits. So our approach, and there have been recent progress in this field, is that to combine these two materials or these two approaches in one hybrid platform, hopefully to have a single hybrid platform that checks all of the boxes. So you can have on-demand sources, you can have efficient detectors, you can operate at telecom wavelength, you can have access to a solid-state qubit. But obviously there is a lot of work that needs to be done to mature this technology. And I will show you the preliminary results that we have so far, and I will highlight also some of the challenges. So again, our goal is to have a silicon-based photonics. Basically, silicon-based materials provide high refractive index contrast, so you can miniaturize the photonic circuits. It's inexpensive, low loss, and it's well-established field now with the fabrication processes. So we would like to have one chip that generates, manipulates, and detects light on the same chip. So now for the on-demand sources, with atoms, you are fixed with these transitions that you have in nature, and the size of the atom is around 1 angstrom. But if you can engineer the wave function of electrons and holes in a semiconductor material, you can actually control the emission or the transition energy between the discrete energy levels in artificial atoms. And I give example here for these quantum dots, which have typical size of 20 to 500 angstrom. You have electrons confined in the conduction band and holes confined in the valence band. And now if you excite the electron hole pairs or excitons in the quantum dot, you can, as they combine, and if you have a direct semiconductor, you can emit a photon with the same energy as the difference in energy between the conduction band and the valence band. So this provides means of having on-demand emission. So once you excite the quantum dot or your artificial atom, it relaxes to the ground state, and you get an emission of photon on demand based on your excitation. One issue actually, and one challenge with these artificial atoms is that they usually emit in a 4 pi angle. So you, unless you can have some engineering of the density, optical density of states around the emitted photons, you will have a lot of inefficient emission. So basically you will lose many of the photons that are emitted from the artificial atom. So the one way of circumventing this or helping to tackle this inefficiency in the single photon emission is to engineer the optical density of states. Basically, if you couple to the artificial atom to a cavity or a one-dimensional photonic waveguide, you can direct the emitted photons with high efficiency to these guided optical modes. So our quantum emitter of choice to tackle this issue is a nanowire quantum dot. This was grown by our collaborators in Canada from the Canadian Research Council. So it consists of an indium phosphide nanowire with an indium arsenide phosphide quantum dot, and you have an indium phosphide shell surrounding the whole nanowire. And the beauty of this structure is that you have very large index contrasts between the indium phosphide and the surrounding air in this example, and you can form like a guided waveguide for the photons that are emitted from the quantum dot to directly couple into the front side or the back side from the nanowire. And our group and others also around the world have been working with these nanowires. They have very nice properties. For example, they show directional, bright and pure single photon emission. So you have very low probability of multi-photon emission. Also, due to the shape of the nanowire, you get Gaussian mode profile, so which makes it also relatively, I don't want to use the word easy, but also possible to couple them efficiently to optical fibers due to the matching between the Gaussian emission profile and the mode profile in an optical fiber. Also, you can, I will not explore this part in the presentation, but you can also get entangled photon pairs directly through the cascade of bi-exciton-exciton emission in these quantum dots. So they are very interesting sources to look at, and we would like to also integrate them in photonic integrated circuits. Previously, most of the research was based on free space optics, and we wanted to explore moving into the integration regime. So this is the idea that we had when we started this project, is that if we can pick and place using a pick and place technique, put the nanowire in an integrated photonic circuit and somehow build the photonic circuit with respect to it. And you see here, this is a schematic of the nanowire sitting inside a silicon nitride waveguide. And as you excite the nanowire, you will get photons emitted on demand based on your excitation of the quantum dot directly to the guided guided mode in the silicon nitride. So this is a small movie showing this process. So we built a nano manipulation setup in our lab. So it consists of basically a needle with around 100 nanometer tip diameter. And you can pick the nanowire due to van der Waals forces and then place it on a photonic circuit to fabricate the waveguides or ring resonators with respect to it. And if you see this movie, is it running now? Yes, so basically you see now we are nano manipulating the indium phosphide nanowire on the facet of photonic crystal fiber, and you see the nanowire is moving basically due to our movement of the needles, and we can do this process relatively in a precise fashion, so we can place the nanowire within 200 nanometer precision with for a fixed point in the circuit. So, but how do we fabricate photonic integrated circuits based on these? There are silicon based on these indium phosphide nanowires. So we start with a silicon wafer with an oxide layer, as you see in here. Let me get my pointer. So this will work as the bottom cladding of our waveguide, and then we deposit some metal to make the marker fields. We drop the nanowire using our nano manipulation technique. We perform imaging from the top of the nanowire to image the nanowire with respect to the marker field. Then we deposit silicon nitride, which will work as the guiding material for the waveguide that we are using. In this case, it's silicon nitride. Then we perform electron beam lithography and reactive ion etching to form the waveguide around the nanowire in here. And this is an optional step, so we can cover basically the nanowire, the waveguide nanowire hybrid structure with PMMA or silicon oxide to provide symmetric mode confinement for the optical mode in the waveguide. This is now an SEM image, as you see in here, and I highlighted where the quantum dot is. So this is basically given to us by the collaborating group that grows the nanowire. So it's basically located around 200 nanometer from the bottom of the nanowire, as you see in here. Let me get my charger. Yes. Good. Now, next to we fabricated the circuit, and you see here a microscope image of the nanowire sitting inside the silicon nitride waveguide, and we can excite it from the top or either in plane, and we can couple the emission in the forward direction and the backward direction. And you see here in this blue spectrum, you see the forward emission, and the red one shows the backward emission, and there is a ratio of around 3:4 in the emission compared to the front port or the back port, due to the difference in the tapering of the nanowire. So typically the nanowire is more tapered in the growth direction, so you get more efficiency in coupling photons out of the indium phosphide nanowire. And we also have relatively high coupling of 24% of the emitted photons into the guided mode. As you see here, we imaged and we did spectroscopy on the nanowire in plane and out of plane, and we have more than the majority of the emission actually coupled into the guided mode. And one question actually came to our minds when we started this project is that despite all of the fabrication steps, so we broke the nanowire from the growth step, we deposited silicon nitride using plasma enhanced chemical vapor deposition. We did electron beam lithography, and we did reactive ion etching. So we wanted to prove that we still have high quality single photon emission. And we did an HPT measurement, and clearly we see that this is a typical value of the second order correlation function that we have for as grown nanowires or fabricated. So we see that the nanowires actually did not deteriorate due to the fabrication steps that we took. Also, we took this further, and we fabricated multiple nanowires on the same chip. So as you see here, 6 nanowires were transferred and 6 waveguides were fabricated, and we can excite them either in plane or out of plane using above band excitation and also quasi-resonant, as we will show you in the following slide. And one thing that motivated us actually to do the quasi-resonant excitation is that we have very good laser rejection. As you see in here, we place so we can excite the nanowire in a waveguide that is perpendicular to the collection waveguide. So basically, we have very strong rejection of the input laser. And in this example, we excite the nanowires with the helium neon laser, and we see no trace of the laser actually in the quantum dot emission. And the filtering of the laser is one of the main challenges actually that faces quantum integrated photonics, that will usually, if you don't do it properly, you can blind the superconducting single photon detectors that Mark was talking about, and I will also briefly discuss in my presentation. So we also did some quasi-resonant excitation of the nanowires integrated in the waveguide. Typically, we excite them with above band excitation, as you see in here. But in this case, we used 870 nanometer, and we got reduction in the full width half max of the nanowire. So the main goal is actually to do resonant excitation and explore light matter interaction in high coupling efficiency structures. So the next thing we worked on is filtering actually, and working on the dual rail coding that Mark was discussing. We fabricated a ring resonator, as you see in here, and the ring resonator, you can couple the emission from a waveguide integrated nanowire into the through port and the drop port. And in this case, we can tune the ring resonator using electrical heaters. And by the end of the presentation, I will show you another approach of actually doing this. So we fabricated a ring resonator based on silicon nitride with a free spectral range of around 1 nanometer. And by heating, by putting current into the heater and changing the refractive index of the ring resonators through the thermo-optic effect, we can start with an emission of the quantum dot, where you have here an exciton line or a trion line. I will not go into the details of here, but these are different emission lines from the quantum dot depending on the number of particles involved in the recombination process. And if you start now tuning the ring resonator, at some point you can couple the exciton line into the through port and decouple it from the through port and couple it into the drop port. And now if you increase again the voltage, you can align another resonance of the ring resonator to the trion line and make it disappear completely from the through port and make it appear in the drop port. Again, here looking at the drop port, we don't see any trace of the laser, despite having much higher laser power, of course, compared to the single photon emission. And this motivated us actually to benchmark the performance of our single photon filter here compared to a tabletop spectrometer. So we started with a spectrometer filtering. So this is a 750 millimeter, so 75 centimeter spectrometer that we use to filter a single transition from the quantum dot, bypassing the on-chip filter and doing an HPT measurement. And we see this is the performance that we would like to beat. So this is the G2 value based on the spectrometer filtering at tabletop. So now we completely bypassed the spectrometer filtering using this removable mirror, and we only use the on-chip filter, the ring resonator, to filter a single transition from the quantum dot. And we see that we are not very far off. So we are very happy actually with these results. And keep in mind that there is a difference of around 10 to the 6 or 10 to the 7 in size between the monochromator that is tabletop and the ring resonator, which has around 140 micrometer diameter. And just as a sanity check, we use no filtering at all, and we see that we have Poissonian statistics, meaning that you don't have single photon emission or quantum or non-classical emission from the quantum dot if you don't have the filtering from the ring resonator nor the monochromator. Also, we investigated doing the wavelength division multiplexing. So we integrated 2 nanowire quantum dots into the same waveguide with a single filter. And based on the settings of the filter, we can tune the ring resonator to either couple quantum dot 1 or quantum dot 2 to the drop port based on the alignment of the resonance frequency of the ring resonator with the emission wavelength of the nanowire quantum dot. So now detection, Mark actually talked about this briefly. So regarding detection, we use also superconducting single photon detector. So it's basically made of a nanowire of a superconducting material. And as soon as a photon impinges the superconducting wire, it breaks the superconductivity and the resistance goes up. So you get a voltage peak at the output. Our goal was to have a full quantum transceiver with on-chip filtering and on-chip source and on-chip detector, as you see in here. So our detector is made of niobium titanium nitride superconducting detector coupled evanescently to a silicon nitride waveguide. The quantum emitters are non-wire quantum dots that are transferred using our nanomanipulation method. Then they are coupled to a silicon nitride waveguide with a ring resonator filter. And as you see in here, we can measure the quantum dot spectrum actually in the waveguide, and we can measure the lifetime of the quantum dot despite having the highly intense laser pulses that excite the quantum dot directly on the chip due to our efficient filtering process on the photonic circuit. So now, after we worked on the detectors, there's a challenge of integrating multiple superconducting single photon detectors on the same chip. So as an example, I show you here the recent work that we did of integrating a multi-pixel detector. So this is a 4-pixel detector coupled to an optical fiber. And if you send single photons through the optical fiber, you can measure an HBT measurement actually between different pairs, and you still get sub-Bostonian statistics. But the challenge is that you need independent microwave lines for biasing and reading of these SNSPDs on chip. So one solution that has been explored in literature is to work on multiplexing of superconducting detectors, and there have been different approaches, either amplitude-based or doing it in the frequency domain or the time domain, as was proposed in this 2013 paper. So the main idea is that the superconducting detector is actually a transmission line, so you can engineer the transmission line to change its group velocity and borrow the ideas that have been well developed in the photonic crystal community and transfer them into superconducting circuits to multiplex detectors. And this is what we came up with. So we designed a 1D, one-dimensional photonic crystal superconducting circuit. So it's basically a periodically loaded capacitor, as you see in here, connecting two pixels, as you see in here. So this is a proof of concept. So this is pixel 1, where you will have the detection, and this is pixel 2. And connecting the two is a periodically loaded transmission line that can modify the group velocity or the dispersion relation of this transmission line. So basically, we can have high transmission, and then as we approach the band gap, the group velocity goes very small, and the group index shoots when you approach the band gap. And we wanted to explore this slowing of light or microwave signals effect to multiplex the two detectors or separate them in time domain. And this is now the experimental results. So we designed the transmission line based on this periodically loaded capacitor, and we were able to achieve group velocities actually of around 1,000 times smaller than the group velocity of, or than the free space velocity of light. So basically, we can delay light by 1.7 picoseconds per 1 micrometer of propagation on the chip. And as you see in here, by increasing the number of loading capacitors from 0 to 30 to 60 to 80, we can separate the detection pulses of the two detectors. And this will give us means to actually use one actually coaxial line to address two superconducting detectors on the same chip and tackle this scaling issue. So, but now it's a bit of contradiction. Like I showed you a tuning of photonic integrated circuit using thermal tuners, but also I said that superconducting detectors need to be operated at cryogenic temperatures. So, but these two things cannot be done at the same time. So we wanted to explore different types of tuning to modify the properties of the optical circuits and the single photon emitters. So we investigated strain tuning, and this is also a new hybrid approach that we took to integrate piezoelectric crystals, PMN-PT in this case, with regular silicon nitride photonic integrated circuits. So we start with PMN-PT, we polish it, and we actually build our photonic circuit directly on top of the piezoelectric crystals, and as you see in here. So we deposit some oxide layer, deposit our guiding photonic layer. It's basically silicon nitride in this case. We do E-beam lithography and etching to form the photonic circuits, and then we use hybrid approach to transfer our single photon emitters. And this is an SEM image of of the devices. This is a top image showing the nanowire quantum dot coupled to a silicon nitride waveguide. And this is a cross-sectional view showing oxide. This is the gold used for the strain tuning or applying the voltage across the piezoelectric crystal. This is now the oxide. Number 3 is the oxide, which is the bottom cladding layer, and silicon nitride is the guiding waveguide. And as you tune the voltage now across the piezoelectric crystal, you can transfer the strain that is generated within the piezoelectric crystals into the upper photonic layers. So in this example, you can tune the emission wavelength of a nanowire quantum dot, and the system shows very high stability. And our goal actually hopefully in the near future to couple it to atomic memories showing this, that the stability hopefully is sufficient. And we can also, in addition to tuning of single photon sources, we can tune photonic elements, the passive photonic elements on the circuit, like ring resonators. As you see in here, as we tune the voltage, we can change the resonance frequency of a ring resonator. In addition to our effort to using piezoelectric crystals, we used actually a more traditional approach, and this project was actually led by Carlos and Samuel, to use MEMS technologies, which is in line, I guess, with this summer school, to tune the photonic integrated circuits in this example. And the circuits are consisting of a grating coupler and a superconducting single photon detectors. And as you tune the MEMS cantilever, you can couple and decouple the superconducting single photon detectors by changing the coupling ratio between the waveguide. And we can get a power ratio of around 28 dBs between one superconducting detector to another. And using this device, we will manage to achieve measurement of an HBT with an on-chip single photon detectors that is now controlled using MEMS technology and commercially available superconducting single photon detectors. And we can tune the MEMS devices at will to couple in and out of a superconducting detector on the chip. So back to our goal. Actually, the goal was to have a hybrid photonic integrated circuit, and then that will contain on-demand sources, some photon manipulation elements like ring resonators or directional couplers, and in the end, superconducting single photon detectors to detect the photons. And so far, we have achieved these technologies by having nanomanipulation technique to transfer the nanowires, strain tuning or MEMS tuning that is compatible with the cold nature of the superconducting single photon detectors, and also SNSPDs that are evanescently coupled to the waveguides. Last thing I want to end with this today is, what about room temperature? Can we do all of this work at room temperature, especially that even our single photon sources, unlike the ones that Mark was discussing, they require operating at cryogenic temperatures, the quantum dot sources. And actually, yes, so there has been a recent interest in and advances in hexagonal boron nitride emitters, and these can emit single photons at room temperature, and then you can actually engineer these emitters by different waves. But in our case, we used the simple method of introducing the emitters using thermal annealing. So we start with this solution that contains hexagonal boron nitride flakes, and we deposit it actually on a photonic chip that doesn't have waveguides yet, but I will go in the process in the next slide. So if you anneal it and we keep the temperature at 800 degrees, then we cool down, we can see that we introduce single photon emitters that can operate at room temperature, show sub-Poissonian single photon statistics. And they operate, we measure them actually at room temperature and also at cryogenic temperatures at 200 millikelvin, and we get a reduction in line width due to the suppressions of phonons of up to a factor of 10. And we did also the HBT showing single photon emission both at room temperature and both at cryogenic temperatures. And the beauty of this, and this is unfiltered. Unfiltered meaning that you don't need to directly filter out the transition that you are measuring. So all you have to do is block the 1550 laser that we are using to excite the HPN, and take all of the emission across all of the emission wavelengths directly into the two APDs, and you will still get sub-Poissonian statistics. So how do we integrate them deterministically into waveguides? So we start with a photonic chip with a marker field. We drop cast HPN on the sample, and then we do thermal annealing to activate these quantum emitters. And then we do imaging to locate these thermal emitters, these HBN single photon emitters with respect to the marker field. And then we do some correction for our imaging system. We have a computer algorithm to actually correct for any aberrations in our imaging system. And then we do electron beam lithography and etching to form waveguides with respect to these HBN emitters. And as you see here, this is an SEM image of a silicon nitride waveguide with an embedded hexagonal boron nitride deterministically integrated in the center of the silicon nitride waveguide. And we excited these HBN emitters from the top, and we can also do it in plane through the waveguide. And we saw that we can locate the HBN emitter before and after the waveguide integration from the top and through the waveguide. And one of the important things of having a deterministic process is that you can control the dipole orientation of the emitter with respect to the optical mode that you are dealing with. So here, ideally, you would like to align the optical dipole with the TE or the TM modes. And since the HBM is in plane, you would like to align it actually with the transverse electric field mode in the waveguide. And as you see here, we have around 4 degrees difference from the ideal positions, and we were happy actually with these results that we can, in principle, align the dipole deterministically based on measuring the HBN before we integrate the photonic waveguides. And also the HBN emitter shows high purity despite the fabrication steps, and we still see less than 0.3 multiphoton emission probability at 0 delay with the HBN emitter integrated in the waveguide.
I'm sorry, Ali, we are running out of time.
Actually, I'm done. So this is our vision thanks. So this is our vision for the future. We believe that not a single system actually can achieve all of the tasks that we need in future quantum photonic systems. So in principle, some of the materials enable large scale integration. Some of them provide very small losses for long delay lines. Some of them provide the possibility to do wavelength conversion, and others provide means of optical memories. So we believe that a hybrid system is the way to go to tackle these issues. And I encourage you to read this review paper that we wrote last year in Nature Photonics. And thank you so much. So I think I'm done. And please join us if you find this interesting.
Okay, thank you very much, Ali, for this very interesting talk and these very exciting results actually. And my feeling is that you could present for another couple of hours further results, which could be of interest for the audience. But unfortunately, we run out of time a bit here. So there are a couple of questions in the question and answer window. And it would be great if maybe after, or let's say in the next few minutes, you would just be available and give the answers directly into the chat. Thank you very much for that. And thanks again for joining the summer school and giving this great presentation. Thanks a lot.
Thank you so much.
Right. So our next and third presentation is an invited talk on non-von Neumann photonic computing for machine learning and artificial intelligence. And it's my great pleasure to welcome Harish Bhaskaran, who is Professor of Applied Nanomaterials at the University of Oxford and leads the Advanced Nanoscale Engineering Group. He holds the EPSRC Fellowship in Manufacturing. His research is primarily in the exploration and use of optoelectronic materials to create photonic or nano or neuromorphic computing and displays, as well as additive manufacturing techniques to take such devices into the manufacturing realm. He made key contributions, including the demonstration of atom-by-atomware, a novel optoelectronic framework, a photonic non-volatile memory, and recently the development of photonic synapses and computing. He is an active innovator and has established 2 spin-out companies. Harish, we are looking forward to your presentation.
Great, thanks very much. I really appreciate the opportunity to talk today. And I thank the organizers for organizing a phenomenal conference here. I shall very shortly try and share my presentation, which hopefully you can see. So do you see the full screen or do you see the presenter view?
It's working.
It is working. Excellent. Great. Then I'll get right to it. So it was an excellent talk by Ali.
So sorry, not yet. It can be seen. It just says that you started to share your screen. Now we've got it. Okay, thank you.
Great, fantastic. So as I said, it was an excellent talk by Ali, and many of the concerns that he shared about photonic circuits in the realm of quantum computing is also shared by non-quantum computing aspects of photonic computing. And I think you'll see a lot of the parallels here in this talk, hopefully. So the title of my talk is Non-von Neumann Photonic Computing. And of course, nowadays we have to add for machine learning and artificial intelligence in everything. But really, let's talk about why we need new forms of computing, given that computers have been around forever. It's mostly because we store everything on our phones and we take a lot of pictures that we never look at. Right. So our data sphere is expanding dramatically. It's expanding to 175 zettabytes by 2025. And currently, artificial intelligence applications generate about 80 exabytes a year. And we expect that to expand by more than 10 times in just 5 years by 2025. So the amount of data we are generating is growing dramatically. And of course, no human being can process all this data in order to create information, because data is obviously not information, it has to be crunched. And crunching that data requires computation. And over the years, anyone who's been half awake has heard of Moore's law. And we know that Moore's law basically means that you scale the size of the transistors down such that for a similar area on silicon, your processing power goes up dramatically without changing the power required for that area to be processed. So effectively, scaling gave free gains because you didn't use more power, but you got way more computation for a long time. And everyone knows that Moore's law is sort of dying or dead by now. But still, if you look at the staggering growth of our processor performance over the years, you can see that between 86 and 2003, the processor performance grew by 52% a year, right? That's the annual growth rate. And even today, at a much, much reduced rate, it's still growing at 3.5% per year, the processor performance. Now compare that to what happened to the memories, right? Memory growth has been really bad, right? It's basically grown at about 7% annually, while processor performance grew at about 52% annually for a very long time. And thus, there was a huge performance gap between your memory growth and the ability of your processor growing at an annual rate. Right. And this created something called the memory war. And this is actually quite important, especially when you're beginning to crunch data. And that's because, and actually that's one of the reasons, if you look at current computational paradigms, especially in hardware for artificial intelligence, I think it's fair to say that our AI computing efficiency sucks big time. Right. So when I got started in this general field of computation, I was very confused, like perhaps a lot of you out there, if there are any of you like me, between the various terminologies such as artificial intelligence, machine learning, and deep learning. And it took me a while to really understand what the differences were. And one of the pictures that I really liked was a picture put together by Abu Sebastian at IBM Research in Zurich in this paper, where he actually talks about artificial intelligence as a catch-all term that indicates some level of mammalian brain intelligence, within which a subset is machine learning, where we are learning without explicitly programming what needs to be learned. And then within that is a further subset called deep learning, where you have many layer classification, which are many layer neural nets, every layer doing some sort of classification of the data, extracting information out of the data. What is clear is that the hardware that's currently being used for deep learning and the hardware that's being currently used for machine learning exist, but they're not optimal. But even more importantly, no one knows what real artificial intelligence would require in terms of hardware. And that's precisely the area that a lot of people are working on at the moment, developing new hardware for computational tasks that are currently growing exponentially, but we really don't have the right sort of hardware to carry them out. And fundamentally, the issue there is the fact that your data, let me see if I can use, fundamentally, the issue there is we are still using the von Neumann architecture where data comes into the central processing unit and the central processing unit crunches it. But in order to crunch it, it has to exchange information with the memory. And therefore, there's A, communication between the processor and the memory, and B, of course, the speed of the memory eventually might end up determining how much processing you can do. The communication between the processor and the memory is called the von Neumann bottleneck. And that, of course, was a big issue that people have been trying to get around for at least more than a decade now through the use of multi-core architecture in order to parallelize that information transfer. The memory itself obviously is being sped up quite a bit through new research, but that alone is not going to solve the problem until you solve the bottleneck problem. The other thing, of course, is the data is just going through the CPU and getting out of the CPU. So literally you're comparing values with the memory. And this leads to a lot of inefficiencies. In fact, when AlphaGo beat Lee Sedol in a game of Go, it was hailed as machines beating man. Really, if you look at the expenditure of energy there's no comparison. Lee Sedol was sipping a cup of coffee and consuming about 20 watts, whereas AlphaGo was sipping about 1,000,000 watts over the cloud in order to beat Lee Sedol. So really, there is a problem in terms of artificial intelligence, and that really sets the motivation for this new race towards new hardware for artificial intelligence and machine learning. So if you look at this particular diagram here, very simplified diagram, of course, the obvious solution that might occur to you is, why don't we co-locate the memory and the processor using some sort of accumulative memories, right? And why can't we do processing that way? And indeed, that's precisely what our group, what my research group has been working on for many years, but in the context of photonic processing. So very briefly, to give you a quick background on what I call PCOM or phase change optical memory, working alongside Wolfram Pernice, who's currently at the University of Munster, in 2011, 2012, we did a very simple simulation to show that by coupling a little speck of phase change material on top of waveguides, we can change the state of these phase change materials from a more transmissive to a more absorptive state, and therefore modify the transmission of light through waveguides efficiently. Subsequently, Carlos Rios, a PhD student, came along, and he put some of these phase change materials on top of silicon nitride waveguides, and by annealing them on a hot plate to change their phase, he showed that indeed you can actually change the transmission characteristics of the waveguide with these materials. Eventually, as part of his PhD, he decided that hot plates are not very efficient in computing, and therefore he managed to couple light evanescently through the light passing through the waveguide onto the phase change material. And he showed that he was able to store up to 8 levels of transmission within the device, what we call a 3-bit memory. Of course, at this point, although this was a huge achievement and Carlos worked night and day in order to get this, it is worth noting a couple of holes in our knowledge at that point in time. The first, the key one being that at this point in time, if you wanted to go from level 0 to level 2, you needed to know a set of programming pulses that will take you to level 2 from level 0. You're sitting at level 2 and suddenly you wanted to go to level 3. You needed to know a different set of programming pulses. If you wanted to go from level 3 to level 6, you needed to know a different set. Or if you wanted to go to level 4, you needed to do a different set of programming pulses. Effectively, for a single device, you needed to know 8 factorial times of information in terms of the pulse sequences in order to deterministically go between these levels. It's okay for a PhD student who needed very, very little sleep and had an amazing ability to work really hard. But even for them, it's impossible when you start scaling these structures to do computation. So over the last few years, we put a lot of effort into understanding the fundamental mechanisms in order for us to simplify this. And we've had some success here. And the key takeaway message from all this work is that compared to electronic memories, where when you set the state of the system drifts over time such that if you have 2 separate states, you may not be able to distinguish them after a certain period of time. The x-axis here is in seconds, right? compared to these electronic memories using phase change materials, our photonic memories do not seem to drift over time. The second thing is we've done a lot of work in this field, especially Shun Lee, a PhD student of mine, where she's figured out that she is able to go deterministically to any state without any knowledge of the current state. So all you needed to know is know which state you want to go to, and you can get there without knowing a complicated pulse sequence using a single pulse operation for write and erase. And this helped us get to, in this particular case, 5-bit operation of this memory with very high repeatability. So armed with this knowledge of our phase change materials and how the system works, we were then able to do a lot of photonic computing, very basic photonic computing, I must add. So in the first case, Wolfram Pernice's group, in collaboration with ours, showed that they were able to do some sort of optical abacus, which is very simple accumulation, where you accumulate the state of the material depending on the number of pulses that passes through it. And then you can do some sort of addition and subtraction, multiplication, which of course is just sequential addition and division through some complicated roots. A former postdoc, Zhengwang Cheng, showed that you could also configure these as synapses. And these synapses completely satisfy the spike timing dependent plasticity rule of synapses. And these were photonic synapses. And then finally, we carried out some sort of in-memory multiplication using these devices. And this was work done in collaboration with IBM Research in Zurich, particularly Abu Sebastian's group, who had worked on the electronic counterparts of this for a very long time. And this works, the mechanism of operation of this is very straightforward, but very powerful. So here you have a waveguide, right? And you have a little block of this phase change material that sits on top of the waveguide. The light that travels through this waveguide interacts evanescently with the material here. Now, depending on the state of this material, which is either more crystalline or absorptive, or less crystalline or transmissive, the transmission is modulated. So you have two numbers to multiply, let's say P1 and P2. You program P1 into a mapped state of the material. So the state of the material determines the transmission, and that is mapped to the number P1 that you wish to multiply. The number P2 is encoded into the amplitude of a very low power pulse that doesn't damage this material that goes through the system. Right? And and that amplitude gets modulated by the state P1, and the output is simply proportional to the multiplication of P1 and P2, and you can map the system for every device. So you can do this for a single device, and if you can do this for a single device, then you can start scaling it up to do it for entire matrices. And this is extremely powerful, because if you really look at machine learning effectively is matrix vector multiplication, where the matrix elements are fixed for a whole round of multiplications, and that can be fixed or stored with this in-memory element. And you have a lot of vectors going through the system that's getting multiplied. Right? And so we've done a lot of work taking this concept into scaling it up and doing some work with it. So one of the first things I'll say is our initial instinct was we would do some sort of spiking neural networks with a system like this using traditional ring resonators. So in this particular case, you have a whole bunch of ring resonators, and you can basically use these ring resonators to pick and choose wavelengths depending on the resonances. And then each of these elements are configured here. They act as synapses. In this case, you'll have 4 synapses, a bus, and so long as the total power coming out of these synapses exceeds a certain threshold, the PCM here switches, and when it switches, you fire the neuron, and you can have these bunches of neurons in order to drive some sort of a neural network. Now, this is obviously very powerful, and we were able to do some sort of classification tasks with this, and this was published just a couple of years ago. One of the issues we realized was scaling up ring resonators is very daunting. We could do it at a lab scale, but beyond that, it becomes extremely complicated. We started using commercial fabs in order to scale it up, and we found that the ring resonator FSRs do not really match, and there's limited scalability. And it's also very power consuming if you have to use heaters eventually to control the resonances of these string resonators. So we had to come up with some other way of doing it, and that was the use of directional couplers, where each of these directional couplers are configured in a way such that the power dropped across each of these columns is very similar, is equal. And so you have these rows which are feeding in the vectors, and you have the columns which accumulate the multiplication addition operation as the MAC operation across each of these columns, which then get added up at the output at the photodetector. This design was done by Nathan Youngblood, who's now an assistant professor at the University of Pittsburgh, and it was scaled up and done by Johannes Fellman, who was a PhD student at Munster then and is a postdoc in my group at the moment. This gives huge advantages. Firstly, there are no resonance structures, which enables us to do fabrication a little bit more simply, and it requires no thermal tuning. Therefore, it's very scalable, right? And this is what was done here. So Johannes fabricated this device. This is a 4x4 matrix where the phase change element is configured at the intersection of each of these elements. So in this particular case, it is in this particular directional coupler here. And then we have another waveguide that is coupled to this phase change element here. And that waveguide is used to set the state of the device. So effectively, that waveguide is used to program these matrix elements. And once you program, then everything else occurs through the rows and the columns. The matrix multiplications occur through the rows and the columns. So then you can, this is your matrix, which is set into the states of the device. You send vectors through the device, which get multiplied, and your outputs are the Y's here along the columns, right? So once you have a matrix like this, you can start doing convolutional neural nets, simply because these are known to show the highest accuracy in classification tasks, but also because they're very well suited to photonics, where the size of our elements at this point was still fixed out, we're still small. So we need something that works with smaller matrices, and our matrix elements are fixed. We don't want to go and reprogram each of the matrix elements very frequently. And this is a very straightforward convolutional neural net where you have an input image that goes through a filter, and the output essentially reduces the parameters of the image, right? And you can use this, for example, to do edge detection. In this case, you can take the image 4 and you can run it through, we used a 9x4 matrix, and each of these columns had one of each of these columns were configured to detect either the upper edges, the left edges, the bottom edges, the right edges, and then the whole matrix detects all of them, and you can combine all of them just to show the edges. So it's a very simple convolutional neural net. We showed that with these 9x4 matrices. But of course, photonics offers something that electronics cannot, which is the fact that because we use light, we can do multiplexing, wavelength multiplexing, which is we can send multiple wavelengths of light, none of which interferes with each other, and therefore you can do parallelized operations of matrix vector multiplications. And that is exactly what we showed in this particular example here. Here you have a image that we wanted to do convolutions on, and we sent 4 convolution matrices. In this case, the edge detection for the right and the left and the bottom and the top. And you can see that on the right and the left convolutions, you can see the edge detections of the vertical lines on the bricks. And on the top and the bottom, you see the edge detections of the horizontal lines on the bricks behind here. And you can put all of them together in order to get the total image, the edges of this particular device. And this whole thing was done in parallel using multiple wavelengths running through each of these rows. And we generated each of those wavelengths using a frequency comb in collaboration with Tobias Stuppenberg's group at EPFL. So this was really meant to show that photonics has huge advantages in applications where you need to do parallel processing to get very high throughput, because you can do wavelength multiplexing, which is very challenging in electronics. Now, of course, I started this talk saying that we're doing integrated photonics on a chip, but this was a huge experiment that Johannes carried out, and it was an extraordinarily complex experiment. And as you can see, very few things are integrated. The chip is sitting somewhere here, if you can see my laser pointer, and you can see the complexity of the experiment in terms of just the sheer components that are required. all around it. And this actually tells you that A, this was an extremely challenging experiment, and B, there's still a lot of work to be done if photonics needs to enter the mainstream and challenge integrated circuits in any reasonable way in terms of all the peripheral circuitry that we need to build in order to build real systems, right? And one of the key challenges there, of course, is to be able to talk to electronic systems. So we need some sort of optoelectronic conversions that are efficient out there. And that's what I'm going to talk in the next 5 minutes of my presentation. So phase change materials are powerful in many ways because they actually can be programmed electrically as well as optically. Right? So the question really was, A, can we use that duality to do something interesting? And B, of course, is can we do other sorts of integration if we wanted to do integration? So the first step we had to do was most of our work until now had been working on silicon nitride waveguides on a silicon platform. And the first thing we wanted to check was how would this whole system work if we were to move that into a silicon on insulator platform, which is more compatible with electronics. And that's work that was done by Xuan Li, a DPhil student, and she showed that actually there are advantages and disadvantages of using both, but in general, they're roughly parallel. Both of them work really well for most applications that we need to work in, and that was published in this particular paper. And the second part she did was she said she wanted to remove one level of complexity, which of course meant that the whole design became a lot more complex. And that was that she wanted to remove this particular additional waveguide that went and programmed each of the matrix elements so that we can actually couple light just into the waveguides, and depending on the power, we can actually route right in order to program each of the matrix elements directly. And she achieved this using heater-based Mach-Sender interferometer that routes right into the directional couplers. And if you're interested in this direct weight sitting using dynamic splitting ratio control, look at our IEDM paper from last year, from December last year at this particular DOI. Of course, the other really exciting part is the fact that can you actually program these materials electrically so that you can set the states of the matrices electrically using all the CMOS circuitry that you need, but just through the throughput, which is where optics really excels in optically. The short answer is in principle, yes, but in practice, there are huge challenges. The primary one being that the wavelengths of optics and electronics are very different. The dimensionalities of optics and electronics are very different. Phase change memories typically work when the dimensions are very small, less than 100 nanometers. Optics does not really work well at those size scales. So how do you bridge those size scales in order to work extremely well? And if you do, of course, you can start doing photonic computational memory experiments with these devices, right? So I'm just going to dial back a little bit to say that we've done a lot of work on the duality of electronics and optical properties of these phase change materials. In fact, one of our first pieces of work was using thin film interference and to dynamically change the thin film interference, essentially mimicking some of the work by Mikhail Katz and Federico Capasso, but except that in this case, we use a dynamic material that changes the thin film optical resonance of these materials. And using this, we showed that we're able to create high resolution displays, each of these pictures being only about 80 microns by 80 microns. And all you're doing is changing the state of the GSD, and that gives very high contrast in the optical properties of these materials. The problem really is how do you scale them up to a size where optics can actually see after you pass a single pulse? And there's a fundamental issue here, which is that if you electrically change the state of the device, you form a very small filament. That filament conducts a lot of electricity, and therefore, you basically have a short circuit there. It takes a lot of power in order to start changing a larger volume of material to the crystalline state. But of course, the small filament cannot be accessed optically. So this creates a huge problem in the electro-optical conversions of these particular materials. So again, it comes back to bridging the size scales between optics and electronics, and how do you do that on a chip? And one obvious answer was, can we somehow combine plasmonics with on-chip photonics in order to bridge these size scales? And that was work that was headed by Nick Pharmakidis, who's a current PhD student in the group. And what he did was he created a design where there are two gold electrodes The pink structures are the waveguides, tapered waveguides. And the phase change material sits between these two gold electrodes. And the gap here is roughly about 30 nanometers, so much smaller than the size scales that optics would typically be able to access directly. But effectively, the design is such that these two gold electrodes act as plasmonic enhancers. And therefore, the plasmonic enhancement allows us to read it out optically through these tapered waveguides. They also end up acting as electrodes for the phase change materials. And therefore, we can A, monitor the resistance of these devices, and B, we can hit it with a higher pulse and change the state of these devices. And here you can see that he can monitor, he can change the electrical resistivity electrically while changing the optical transmission optically simultaneously using this mixed mode optoelectronic memory. And so we think that this is a very exciting way to bridge the size scales between optics and photonics while still being able to access what we call mixed mode, the electro-optical transition of these materials in order to be able to see the phase changes. This was obviously done using what we would call direct switching, which is we directly switch the state of the material. Now, of course, that only works if the material is conductive, and you can switch the state of the material easily, readily. What if the material is not conductive, or you want to be able to switch it while decoupling the electronics and the photonics? Well, that can be done with a heater. And Nick has been working on a plasmonic enhanced reheater for many years in parallel. And this is work that he recently has shown, where you have a mini heater here and you have a monitor of the resistance across the nanogap. And effectively, the heater is decoupled from the phase change material. And the heater heats up. You basically pass a current just through the heater, so it's really low resistance, and you can do it at high speed. And that changes the state of the phase change material. And you can use that to monitor the change in the optical transmission through these materials. And we find that it is much more readily controllable, this way of changing the state of the material. And we also get better contrast ratio between the amorphous and the crystalline states. Of course, there's been a lot of engineering done in order to reduce the power, because when you use heaters, the big problem is the power required goes up dramatically. And Nick has re-engineered the power requirement for these heaters quite dramatically, such that they're almost equal to our earlier work on plasmonic nanogap devices. So with that, I'll just say that a lot of the work that we do, of course, is in material science, because electronics has the perfect functional material of silicon. You dope it differentially and you can achieve a lot of functionality. That sort of single element functionality is missing in photonics, and therefore we need a lot of functional materials in order to drive a lot of our innovation in this space. So in this particular case, we showed that single elemental antimony itself can act as a switching or non-linear element, because it goes between an amorphous and a crystalline phase. And we can use this to show that these two states have different optical properties. In this case, just by annealing it, we modulate a ultra thin film cavity, 3 nanometer cavity, and we can change the state of the material such that the strong interference effects change the color of the material.
Sorry, Harish, we are running out of time.
Okay, great. Sorry, I'm done here. And then now we are putting it on integrated photonics in order to be able to switch and reset the matrix elements extremely fast. And one last slide, just wanted to say that since this is the optical MEMS, there's also the NEMS community out there. We also do a lot of work on using functional materials on optics, and at the intersection of optics and NEMS. And in this particular case, it's a nanowire device, a functional nanowire device, which we can see optically having a resonance frequency, and we can change the resonance frequency of these devices or tune it using the functional materials property. So with that, I'd like to conclude by saying that effectively we can use functional materials to do some sort of basic calculations. We have techniques to scale up these devices, and we are working on ways to improve the device functionality by integrating electronics alongside the optics. But it's work in progress in the sense that we are just showing one component of the photonic system. And in order for photonics to succeed, system integration is a key challenge. And we've discussed this challenge in this review paper earlier this year, and it's still a challenge that's not being solved. And I'd like to acknowledge all the collaborators and co-workers, all of whom have done most of this work. I've just sat in my office and sort of told them, well done, in many cases. And Wolfram Pernice, David Wright, and Abu Sebastian have been very good collaborators over the years. Thanks.
Thank you very much, Harish, for that very inspiring talk on photonic in-memory computing. And also in your case, there's a couple of questions in the question and answer window, and I would like to ask you to be available a couple of more minutes to answer these questions directly in the chat window. So thanks a lot once again for that talk.
Thank you.
Okay, so with that, we switch over to our next speaker, which is Professor Jelena Vutkovic. And her invited talk will focus on inverse designed integrated photonics. Jelena is a professor at Stanford, where she leads the nanoscale and quantum photonics lab. She is also director of QFarm, the standard SLAC quantum initiative. She has won numerous awards, including the IETAF Harvey Prize, James P. Gordon Memorial Speakership from the OSA, Humboldt Prize, the Distinguished Scholar Award from the Max Planck Institute for Quantum Optics, Hans Fischer Senior Fellowship, the Presidential Early Career Award for Scientists and Engineers, and the Young Investigator Awards from DARPA and the Office of Naval Research. She's also Fellow of the American Physical Society, of the Optical Society of America, and of the Institute of Electronics and Electrical Engineers. Jelena, it is great to have you here as a speaker, and we are looking forward to your talk.
Thank you very much, Harold, for the kind introduction, and thank you and Dan for also inviting me to speak here. And well, thank you all for listening. I'll talk about our recent work on inverse design. I'm sure some of you at least have heard me talk about that because this is something that my group has been working on for more than 15 years. But in particular, today I would like to address some of our recent work on integrated photonics implemented using inverse design, in particular using commercial foundries. So the idea here, as I said, is basically to implement better photonics than traditional photonics approaches, better device performance, new functionalities, smaller footprint, higher efficiencies, elimination of brute force design from the design process. And again, as I said, this is something that my group has been working on for a long time, pretty much since I started as a faculty, because we wanted to eliminate all of the uncertainties in the design process and fabrication process. We wanted to build optimal devices and also the devices that would be immune to environment and fabrication errors, so that you don't really need to post-tune everything and fine-tune and tweak when you make an integrated circuit. And that way you can enable better functionality and larger scale integration. And in the process of doing that, I mean, we initially started with some simple two-dimensional designs, but of course in photonics, you have to design things in 3 dimensions, nearly all of them. So about almost a decade ago, we managed to develop a design process for arbitrary 3-dimensional photonic devices, where we can efficiently search through the full 3-dimensional parameter space of fabricable designs by using a combination of fast electromagnetic solvers and classical optimization tools, the same type of optimization tools that people use in, other processes, and also AI. And that way we could actually design a variety of devices, including kind of the one that you see behind me and also on the screen, which is a wavelength multiplexer, demultiplexer implemented in silicon. And if you're new to the field of the inverse design, where we basically design devices based on the figure of merit and function that we would like to implement by combining these AI tools and optimization tools with fast solvers, we wrote a review article with Alejandro Rodriguez from Princeton a few years back, which describes this booming field of inverse design in photonics. So here, basically some of the first experimental results that were achieved using this approach. We started by designing individual devices, such as wavelength splitters, mode converters. Initially, we would design them in such a way that we could fabricate them using our fabrication facility at Stanford. And these are devices implemented in silicon on insulator. This is a 2-channel wavelength splitter on top and 3-channel wavelength splitter on the bottom. Very compact, 2.8 by 2.8 microns for top, 4 by 5 microns for bottom. And on the right, you see experimental performance. And what is very exciting here is that on the right, we show experimental performance for many devices fabricated with nominally the same parameters. And without any post-tuning, we actually measure them, and the ones that were fabricated with the same parameters nominally, right, although our process is not perfect, would exhibit the same transmission characteristics. So what you see here are transmission characteristics for many devices on the chip that were measured and just plotted on the same plot without any post-tuning, which was actually very exciting for us because this is not something that you, as you all know, you can achieve when you perform fabrication in a university facility or even in a commercial foundry. You always need some post-tuning to compensate for errors or environmental variations. So that's what we actually started from. But then in recent years, 5 years or more, we started moving more towards integrated circuits and systems, because of course, you know, it's interesting to develop a method and to show proof of concept that you can shrink dimensions of wavelength splitter or mode converter by orders of magnitude. But the process is useless if you have to rely only on kind of proof of concept and low throughput fabrication techniques such as you know, university electron beam lithography and experimental etching techniques. So we wanted to really show that we can build integrated circuits using this approach and that we can rely on commercial foundries. And we've been working with pretty much all of the major photonics and commercial foundries over the past 5-6 years in order to show that inverse design is fully compatible with foundry fabrication. And the results that I'll show you today actually prove that that's indeed the case, which is very exciting for us because it tells you that you can implement this in functional systems and you can reduce footprints of photonic circuits, you can make them more robust to the environment, to the operation, especially in complex photonic circuits. You always need some electronics nearby. They have to operate in real environments. And you can actually also develop new functionalities. You can build more efficient also components relative to the ones that we traditionally use in photonics, which is, of course, a very pressing issue in a lot of applications, and in particular quantum applications when you need very high efficiencies, way beyond anything that's been demonstrated in photonics, or things will simply not work. We have been doing that, and today I'll show you some of the recent results on that. Apart from these individual devices, initially we demonstrated new functionalities. Maybe as an ultimately new functionality, we demonstrated a stage of laser-driven particle accelerator. So that's quite exciting. It's a major collaboration between Stanford and in particularly several universities in Germany on building a shrunk compact version of particle accelerator on a chip where a 3-mile long linear accelerator could be basically implemented on about 1 inch of a silicon wafer. And we showed a single stage of that accelerator, which actually works. It works as well as the radio frequency accelerators. And by cascading about 1,000 of these elements, we could build a whole accelerator. We also demonstrated non-reciprocal pulse router in silicon. I will actually say a few words about that. I will not really have time to talk about particle accelerator, but you're welcome to read our paper. And I will also talk about a variety of inverse design photonics that we implemented in foundries, including on-chip and chip-to-chip optical interconnects. Over the years, since we've been working on this for a really long time, we developed software suite, which we call SPINS, Stanford Photonics Inverse Design Software. It can be licensed from Stanford. A lot of companies and also government labs and academic groups around the world are using this software for design. We also have open source basic version on GitHub at the link shown at the bottom right. This is the basic version, doesn't have all of the features, but of course, a lot of people are also downloading and using it for some proof of concept designs. So now let me move on and say a few words about the foundry fabrication. Process of designing structures for foundry is pretty much the same as designing them for university fabrication, but you have to incorporate design rules for a foundry process. And the process is really shown here. You start from some design rules that you know about the particular process. You design structures by searching the full parameter space, but by satisfying those design rules. And once you produce those layouts, you can send them to a foundry for design rule check. They can implement devices using their process, and then you can test your devices. I have to mention that although you here see two-dimensional layouts of the devices, we design everything in 3 dimensions. And design of something like this here, which is on the order of 3 by 3 microns in linear dimension and vertically also several microns, or the structure behind me, would take only on the order of few hours on gaming GPUs. So you don't really need a supercomputer. We developed everything so that you can use very hardware which is inexpensive, that costs only a few $1,000s. And it is important to mention that in the process of doing this, we go through thousands of electromagnetic simulations in series, which tells you that electromagnetic solvers that we developed are also orders of magnitude faster than any commercial electromagnetic solvers that you have. So for example, you can take a commercial finite difference time domain tool like numerical and interface it to some adjoint optimization, but then this optimization would take many days or weeks instead of few hours using our approach. And this is really important because if you would like, this is a local optimization, you never know whether you are going to find a solution that satisfies your figure of merit. So you don't want to wait 2 weeks to see that you are not getting to a right solution. You want the process to be really fast. And that's really what we've been doing. And I will not have time to talk today, but we also have a paper on arXiv if you're interested in designing the whole structures, whole meta surface at once without any approximations. Then you can, we showed that our new types of electromagnetic solvers can simulate millimeter size meta surfaces in reasonable amounts of time, many orders of magnitude smaller than commercial electromagnetic tools, which means that you can also optimize the whole millimeter size meta surface in reasonable time. So the first foundry-based results that we obtained were in collaboration with John Bowers from UC Santa Barbara and using AIM Photonics foundry in the US. For those of you, at least from the US, you are probably familiar with it, in upstate New York. Here are some of the initial results. For example, 3-channel wavelength splitter fabricated at Stanford, the same wavelength splitter fabricated in AIM Photonics, exactly with the same parameters, theoretically predicted behavior. And here is the experimental result for the same structures from the foundry. And this is for the many devices on the chip. They all perform the same. There is a small degradation in performance relative to our Stanford results. And that's because the minimum feature sizes in AIM Photonics are 100 nanometers and not 80 nanometers as for our Stanford process. And that's not something that we had known when we sent these designs. Of course, now that we know design rules, we're redesigning structures for particular foundry process. Here is another result. This is spatial mode splitter converter, where you are splitting first order mode to top left port. This is only 2.8 by 2.8 microns. Second order mode converted to first order mode and split to bottom left port. This is done with very high efficiencies. We expect theoretically 1 dB loss per device. This is for cascade of 2 devices in about 200 nanometer bandwidth, so very broad bandwidth as well. And then experimentally, we see about 1.5 dB per device, so 3 dB for cascade of 2 devices, again, as a result of this discrepancy between minimum feature sizes for our process and for foundry process. So those were initial results in the foundry, still device level results. But, you know, since then, and recently in particular, we moved into integrated circuits. And of course, you need to make photonic circuit for any, most of the interesting applications of photonics. So here is a recent result that we're excited about, and we're actually pushing it further. We have even some more exciting results since this one that's already on arXiv. This is a system for optical interconnects, chip-to-chip interconnects and on-chip interconnects, which includes inverse design, and it's a fully foundry-based system. And the idea here is to reduce the footprint of the system and to increase the number of channels for communication by doing multidimensional communication, which means that you are combining wavelength division multiplexing, demultiplexing with mode division multiplexing. And that's not a new idea. You know, of course, using different spatial modes for communication is something that other groups have attempted before. But for on-chip communication, the use of different spatial modes is the problem that hasn't been really solved efficiently. It either requires large footprint or efficiencies of components are not good, which is why we resolved to using inverse design. And this is the system that we have. You can have input different frequencies from frequency comb or mode lock laser. Then you have your system for wavelength division multiplexing, demultiplexing, and then mode division multiplexing, demultiplexing, where different frequency channels are encoded in different spatial modes. And then you can have that, use that either for on-chip or chip-to-chip communication. And I will show you how we implement the mode division multiplexing part. We've been able to demonstrate aggregated data rate of 1.28 terabits per second in on-chip interconnect system as you see in the next slide, using foundry fabricated devices. And this is a collaboration between Stanford, University of Pennsylvania, Firuza Flatouni. At Stanford, we collaborate with David Miller also, UC Santa Barbara, John Bowers, and USC, Alan Wilner. Here is the foundry fabricated system. Again, you here have WDM part. This is mode division multiplexing part. This is inverse design, mode multiplexer, demultiplexer. This is for on-chip interconnect system, 250 micron long waveguide, and then receiver, which is just, again, the same mode demultiplexer followed by WDM system. And this is the performance, continuous wave performance, CW performance of these mode multiplexers, demultiplexers, which shows excellent crosstalk suppression and efficiency of the system. So this is the zoomed in picture of mode multiplexer. Again, you have 4 different input waveguides here because it's a 4-channel, 4-mode system. Each input mode would be converted to different spatial mode at the output waveguide using this very compact component, which is only 6 by 6 microns. And this is the experimental performance for these mode multiplexers. We used 16 wavelengths at the input here and 4 spatial modes, which gives you a total of 64 channels, 16 times 4. And wavelength channels were operated at 20 gigahertz frequencies, 20 gigabits per second, which gives you a total of 20 gigabits per second times 64, 1.28 terabits per second communication rate. And this can equally be used for on-chip communication or chip-to-chip communication, because you can also output all of these different spatial modes via grading outcoupler and either free space or specialized fiber, as I'll mention in a moment, and send to a different chip. So here are the data for 1.28 terabits per second data rate with 64 channels. Bit error rate is lower than 1.5 times 10 to minus 2 without any error correction, which is already quite exciting. And this is for on-chip interconnect system where you transmit data over 250 micron multimode waveguide. We also did chip-to-chip interconnect experiment at lower rate because this was done in my lab and we don't really have equipment for very high speed communication. But here we output different spatial modes using these inverse design grading couplers and send them via free space to another chip. And we show that this also works really well. And we're now collaborated with the group of Dan Maron at Hebrew University of Jerusalem and Corning on basically not using free space for connections between multiple chips, but using specialized rectangular core fibers that Dan's group already demonstrated with Corning that would be ideally suited for connecting different chips and implementing chip-to-chip interconnect system. So that's quite exciting, and we hope to very soon show data for that too. So now, of course, this is just one particular application. You can use different modal bases. You can do a lot of other exciting things with this. This is optical vortex beam emitter, which is interesting for hyperentanglement in quantum communication, or it would be also interesting for particle trapping. Here, you can actually make a very compact optical vortex beam emitter by designing these outcouplers, kind of combination of mode converter and grading outcoupler, which couples the slab silicon waveguide mode to a particular output mode with a certain angular momentum. And here are the designs at the bottom, and here you see theory, how the output mode should look like if you shine light with a silicon chip to each of these designed outcouplers. And on top, you see experimental result. And you see excellent match between experiment and theory. And these are very compact. They are only 3 by 3 micrometers, and they have broadband operation of 60 nanometers, implemented in silicon on insulator, which is not something that you would typically see. This broadband operation is not really trivial to achieve. So here is a broadband operation. Here are the results at different wavelengths for one particular vortex beam emitter. And not only that, you can actually kind of implement new functionalities where you make this outcoupler, vortex beam emitter that multiplexes different inputs and produces the output, which combines inputs, all of these different vortex beams together. So for example, here, you design the system so that when you excite it via the left waveguide, it should produce L equal to -1 mode. If you excite it from the right waveguide, it should produce L equal to +1 mode. And if you excite it from the bottom, it's L equal to 0 mode. And if you excite all of them together, then it's a superposition of these modes. And this is how the design would look like. And that also works. And this potentially has some interesting applications also in hyperentanglement in quantum communication. So now, a few more minutes to show you some of the other functionalities. I mentioned also non-reciprocal transmission and routing. This is, of course, an interesting application where it's not a full isolator on chip, because we all know it's very difficult to put the isolator on chip. It requires magneto-optic materials or dynamic tuning of the structures and takes a large footprint. But for some applications, you can actually achieve pretty good isolation in certain regime of operation. And that's what we showed here, again, via inverse design. And this is based on the proposal by Andrea Alou that you can achieve non-reciprocal transmission in passive structures by combining resonators that have Lorentzian and Fano line shape and nonlinearity. And you can design the system so that in the forward and backward direction, you couple different amount of power to your nonlinear resonator. So that would shift the transmission characteristics of the system and allow you to transmit differently for forward and backward propagation, which is basically non-reciprocal transmission that you need for a lot of applications. And Andrea's group demonstrated this in microwave circuits, but it was difficult to implement this properly in photonics. So we decided to use inverse design to implement the right transmission characteristics. And here you saw the movies of how the design process looks like, where we're just designing the couplers between ring resonators and waveguides. And within an hour, you can do this and design the right transmission characteristics, Fano and Lorentzian, and achieve the right behavior. And here is the measurement, in the right dynamic power range. Forward transmitted pulses going forward are always transmitted. Backward pulses are blocked. And we can do that at up to actually 30 gigahertz operation rate. And outside of that dynamic power range, you are not really blocking backward pulses because you are not really operating in the right regime. And we also use this in the ranging measurements, of course, which is important for LiDAR, where we would block back reflected pulses from target and send them to detector instead of sending them to laser. And with this very small footprint and passive structure, we can have very small insertion loss, 0.17 dB, very high operating speed, very small, again, also footprint, and it works really well. We did up to 60-meter ranging measurements. So that's a new functionality. There are many other functionality. I'll just very quickly go through this one before I show you different materials. This is optical phased array application, which of course people have been looking into in many different configurations, photonic configurations. The idea is to steer the beam at the output and then can actually probe the environment for LiDAR applications, for instance. And there was a beautiful work from Belgium where people implemented conventional optical phased arrays using on-chip waveguides, but they were able to steer the beam at the output of the chip by 15 degrees when they tuned input wavelength by 100 nanometers. And that leads to complex and expensive system because tuning input laser wavelength by 100 nanometers requires expensive equipment. So we wanted to see whether we could steer the beam by more just by tuning the laser input wavelength by less. And we were able to use inverse design to steer the beam by 20 degrees for 20 nanometer laser input wavelength tuning. And of course, this relies on dispersion engineering because the output beam depends on the dispersion of the structure. So we rely on inverse design to engineer dispersion in such a way that we maximize steering of the beam at the output. And this is the structure we implemented. You see some non-intuitive parts, which are optimized converters from regular photonic structures to photonic crystal waveguides, good couplers, and also this is engineered using inverse design, as I'll show you in a moment, to achieve the right type of beam steering. And very quickly, steps here are inversion, dispersion engineering. You really want to draw your dispersion relation between your frequency and the K vector in the structure and manage to optimize the structure to hit that. That has not been possible previously. People have done that manually in photonic crystals, but we now can literally draw design target and achieve it using the optimization tools. We also designed variety of couplers to photonic crystals. That's also a very difficult problem in photonic crystals because of the mode mismatch. You can't couple really well to a lot of photonic crystal structures. We can do that better with these couplers, and we can show that we have the right group index of 25 over 20 nanometer bandwidth as designed. Then a lot of different mode converters between regular photonic waveguides and photonic crystal waveguides as shown here. Finally, we also can design our dispersion engineered structure in such a way that we scatter the right amount of light at the output, desired amount of power. And that's again done by dispersion engineering. And at the end, once you put everything together, you can actually tune the wavelength by 20 nanometers and you steer your beam by 20 degrees at the output as shown here. You can change your structure so that you scatter different amount of power as desired. Of course, this is kind of enabling you to use less expensive tools and more compact geometries for optical phased arrays. So we're quite excited about that, and we're continuing towards the implementation of practical systems. Finally, everything that I showed you today was so far based on silicon. This approach is, of course, applicable to any other materials. We worked extensively with silicon carbide, diamond in my group in the context of quantum optics and quantum photonics. Here you see diamond structures that are inverse designed. These are silicon carbide structures that are also inverse designed. This is useful for building quantum optical and nonlinear optical systems. And it's particularly important, again, for quantum photonics, where you really need very high efficiencies in order to make anything that works. Otherwise, the system doesn't work and you can't scale it. And this is beyond things that we've done in photonics, and there are no known solutions for that. So we can do that by incorporating parameter constraints, fabrication constraints for a particular material, which are of course different for diamond than for silicon. And here you see some successful results in diamond. Here also you see some successful results in silicon carbide that we implemented at Stanford, again, inverse design structures. And here we have quality factors greater than 5 million with loss of 0.08 dB per centimeter, which is 8 dB per meter, kind of getting close to the state-of-the-art results in silicon nitride. And this is silicon carbide and insulator that we make ourselves at Stanford. So more silicon carbide structures. And just to mention that silicon carbide, apart from quantum optics, is also, of course, very interesting material for nonlinear optics, having second-order optical nonlinearity. Recently we demonstrated also single soliton state in silicon carbide with thresholds comparable to other materials. So it's really excellent optical material, nonlinear optical material with strong second and third order optical nonlinearity. And here you'll see that all of those demonstrations already kind of incorporate inverse design structures. So you can use this for metrology and for other applications where people have typically used nitride or also lithium niobate and so on. So with that, let me conclude my talk and say that photonic optimization is critical for implementation of scalable and practical photonic systems. For classical photonics, quantum photonics maybe even more so because of the necessary efficiencies. If you're interested in using our approach, we have this software that you can license from Stanford, full version, or download basic version from GitHub. That's the link, but you can also find it from my group's webpage easily. Let me just acknowledge my group at Stanford, people who contributed to the work and our funding. This is my team, and thank you very much for your attention.
Thank you very much, Jelena, for that very interesting presentation on inverse designed photonic circuits. We actually also have a couple of questions. So let me start with that question here. Can the inversely designed shapes be generalized to the design of active devices?
Oh yeah, absolutely. And that's what we also do. Of course, for active devices, for example, we've done some work on modulators ourselves, and also foundry-based modulators, even where we would like to make more compact modulators and reduce the region where you're doing refractive index tuning. That for active devices, you can design them in the same way, but generally active devices have particular steady states for which you have to design. So geometry is not changing unless you're using MEMS, right? If you're talking about just the refractive index shifts, using some sort of material or free carrier injection. So you're not really changing physically geometry, but you have to design the structure which has different functions for different refractive indices in the same geometry. And mathematically, that's exactly the same problem as design of everything that I've shown, passive structures that I showed you today, where you still have to do multimode optimization to span certain large bandwidth, right? So mathematically, the fact that whether you are handling different modes, different wavelengths at the same time, or you are kind of handling different steady states with different refractive indices is actually exactly the same problem, same complexity. And we've done that. So basically you define for the same geometry for different refractive indices, you have particular function at the output, switching at the output, and you design the structure geometry by setting up that as your figure of merit. Okay,
thank you. I assume that you already worked on active structures too, and actually it comes directly to the next question. So you presented a two-dimensional approach, but in principle, with respect to the fabrication technology, even layer stacks would be possible to shape the light output maybe three-dimensionally. Can you comment on that?
Yeah, absolutely. So, just again, clarification that all of the designs that I presented today were done in 3 dimensions, but we restricted designs to slab of high index material, sitting on low index material, but all optimization is done using 3-dimensional structure, right? Because to capture behavior. And of course, having that said, you can also kind of design arbitrary geometry in the 3rd dimension. That's not something we can fabricate at Stanford, but we've done layered designs for a foundry. And depending on the foundry, global foundries can do 2 layers easily in the process that is accessible to universities, 2 different layers that you are independently you're designing them at the same time, but they have different patterns, like stacking 2 patterns that you have behind me on top of each other. Of course, some foundries have the capability of designing many more layers than 2. And we also work with other groups, other foundries on that, and that's fully possible with the current system and the current actually software tool that we have. Just that the structures that I showed you today would be single kind of 2-dimensional pattern in a single layer, but keep in mind that everything is designed in 3 dimensions. So in terms of time, having multiple layers stacked on top of each other is not increasing the time by much.
I see. Okay. Thank you very much, Jelena, once again for the great talk. There are some further questions in the question and answer window, and I would appreciate if you could answer them now directly after this session. Thank you for that. Thank you for that. Great. Okay, good. So with respect to the audience, I would like to thank you for staying awake late in the night, getting up very early, or just having joined in the afternoon. And a special thanks to our speakers who gave us a great insight into their work in the field of reconfigurable photonic computing. Now we had some preliminary remarks from Dan, and now he has some final remarks. Dan, please.
Okay, I hope you can see me. Is the video coming on? I'm not sure. I'm going to steal the screen.
Yes, we can.
Okay.
No. Sorry, we still see the slides from Jelena.
Yeah, I'm going to try to stop Jelena's presentation, and hopefully mine will run this time. Yes, no.
Same as previous.
Oh, there we go.
Yeah, now we've got it.
So first, excuse me for the problems that we had, a technical glitch. Apparently, PowerPoint got stuck, and I should have just killed it and relaunched it, which causes it to work again. So I'll just briefly run through the presentation. And this first slide basically is a general introduction to the conference Optical Methods of Nanophotonics, dealing with our ability to synthesize structures that allow us to then manipulate light. And we're all heavily invested in this field, and we love it. And these are just some examples of some devices that can be designed using these skills, and we can then use these for various applications. And we've heard some interesting ideas today. As I've mentioned, the conference has been running since 1996, and you can see the really large diversity of locations around the world in very interesting places as well. So do consider joining in the near future when in-person conferences are in effect again. Last year, of course, 2020, we had to cancel due to the virus, and this year we opted for the summer school format. Just to show you how much fun the conference is, these are just some pictures from past conferences. So looking forward to having your pictures in there as well, and joining us in future events. I also want to send a few special thanks to the IEEE Photonics Society for being with us throughout the years and supporting past conferences as well as this online event. And I'm sure we'll be back again in the future in 2022, hopefully in person by then, future meetings. So talking about 2022, as I mentioned, Brazil is the target host for the next conference. Hopefully health situation and travel restrictions will be then cleared away. So we're looking forward to seeing you next year in Brazil. Hopefully things will be well. General Chair will be Hugo Hernandez Figueroa, and hoping to see you there and use that opportunity to see this exciting place in South America. And of course, this year's program, we have 3 days. We just went through the first day. I'm sure everybody's here has gone through all the talks, incredible lineup. We have interesting talks scheduled for tomorrow and the next day. You have all this information also on the website. Do note that tomorrow and the following day, we start on the hour, not 15 minutes after the hour. So it will be 1 o'clock in the afternoon, UTC time, and check your local timings in order to catch everything. So with that, let me conclude. Thank you for attending today. And of course, looking forward to seeing you all tomorrow. And thank you, Harold, for presiding over this session. We have other presiders for the next session, and everybody in the team has helped put together this wonderful program.
Excellent. Thank you, Dan. And once again, thanks to everybody joining this session. And I hope that all of you will join tomorrow too. So have a nice remaining day, night, whatever. Goodbye, everybody.
Thank you. Bye.
Bye-bye, everyone.